Hello and welcome to Sleepy Science. Tonight, we'll drift from proper time to quantum clocks, rising through atomic fountains, listening to Ramsey phases, and feel gravity's gentle redshift on their ticks. We'll share time the quantum way to beat classical limits, bind moments with across-time correlations and temporal bell tests, and try gentle, weak measurements that read between outcomes without waking the system. We'll blur before and after with indefinite causal order. Follow entropy's arrow while letting thermal time and modular flow show how a state can choose its own clock. We'll ask Pauli why a universal time operator never arrives, press rewind with Loschmidt echoes, watch dephasing smear moments and, sometimes, recohere. We'll read the page curve's quiet promise that black holes give information back, feel complexity tick like a second hand, and end by wondering whether we ever needed time at all, or only well-kept change. Tell me where you're watching from and what time it is there. And if these unhurried explorations help you rest, please like, subscribe, and share. Now take a long breath, let your shoulders drop and settle in where curiosity glows and the night teaches gently. Proper time versus quantum clocks. You think you know what time is because clocks on your wall and in your phone agree well enough to plan your day. But physics quietly tells you that time is not a single universal river. It is something you carry with you, and it can flow differently for different travelers. And in the quantum world, it can even tick in ways that make the idea of a single path through life feel incomplete. In Einstein's picture, the most honest readout of duration is called proper time, the amount of time a perfect clock would accumulate as it moves along its own path through space and gravity. And this number depends on how fast the clock moves and how deep in a gravitational field it goes. So two people who part ways and later meet can compare watches and discover that their personal histories contain different totals without either one being wrong. Because proper time belongs to the route, not the map. Now turn that idea toward the quantum world, where a clock can be an atom with two energy levels acting like the hands of a tiny watch. Because the relative phase between those levels winds forward at a steady rate and gives you an exquisitely regular tick. Yet quantum mechanics refuses to pin the atom to a single, neat trajectory the way classical pictures do. And this creates a tension that is as educational as it is beautiful. Relativity says duration is the integral of a path, while quantum mechanics says there isn't always a single path to integrate. To feel the contrast, imagine strapping a flawless wristwatch to your arm and jogging around a track while a friend rests in the stands. Your watch measures your proper time and will lag slightly compared with your friends because you moved faster and felt tiny accelerations. And if you climbed a staircase or descended into a basement, you would add the effect of gravity's pull on your rate, subtle but real, and so well tested that our navigation satellites wouldn't work if we ignored it. That is proper time in action, a reading every idealized clock must respect. But an atom used as a quantum clock marks time by the evolution of its wave function, not by a tiny gear turning. And the phase that does the ticking is sensitive to energy differences, disturbances from the environment, and the overall motion and gravity the atom experiences. So the tick you read out in the lab is not a simple second hand, but the visible fringe of a hidden rhythm that depends on how well you isolate the system and how gently you ask your question. In the classical limit, when you handle many atoms, let them interact with their surroundings, or average over disturbances. The quantum clock falls into line and behaves like a reliable traveler through spacetime, accumulating what is effectively proper time, which is why the best timekeepers humanity has built are quantum at heart, yet serve the everyday role of setting international time. In this regime, the quantum phase and the relativistic duration harmonize, and the world feels pleasantly consistent. The friction arrives when you push beyond that comfortable limit and ask for the reading of a clock that refuses to commit to a single path. If a quantum clock can be placed in a state where it has a chance to take one route and a chance to take another, which proper time is the time it lived through, the honest answer is that you cannot assign a single classical duration to a state that never had a single classical history. And what you can measure instead is the relative phase that builds up between the alternatives. Because phase is the quantum bookkeeper for how different stories disagree. When those stories reconverge and you let them interfere, the shape of the interference tells you about the accumulated difference in their times, which is not a paradox, but a lesson about how time emerges once choices become definite. This picture also clarifies why precision timing is always a battle against noise. The more sharply you try to read the phase, the more the environment wants to entangle with your atom and smear out the rhythm, and that blurring, called decoherence, does not destroy time, but dissolves the delicate phase information that made your quantum tick so crisp. On the other hand, shelter the system carefully, and you get a clock so steady that it can sense tiny changes in motion or height as slight rate shifts, revealing that quantum clocks listen to space-time just like classical ones, while still keeping their uniquely sensitive ear for phase. Notice what this means for your intuition. Proper time is about the geometry of a path and is deeply objective for that traveler, whereas a quantum clock's report can depend on how you prepare it, which alternatives you allow, and how you choose to read the result. That dependence is not subjectivity in the sloppy sense, but a statement that time is partly a relationship between a system and the questions you ask of it, and that relationship collapses into the familiar when many degrees of freedom wash out the fragile details. It also explains why the everyday advice, just use a better clock, eventually runs into conceptual walls, because the act of making a clock better, narrowing its energy spread, isolating it from noise, lengthening its coherence, pushes you toward regimes where your old classical story about a single ticking object along a well-defined track stops being the right language and must give way to the quantum story of phases, amplitudes, and information. If you are wondering which description is more real, take comfort in how they meet. When your clock is macroscopic, jostled by air molecules bathed in light, and constantly observed by its surroundings, the quantum rhythm is forced into a simple, classical beat that counts proper time along your world line. When you minimize those interactions and treat the clock as a quantum object, the beat is still there, but it belongs to a chorus of possible paths, and you learn about their differences by listening for interference rather than reading a single dial. There is a gentle humility embedded in that realization, because it tells you that time is not a master schedule posted in the sky, but a rule your world and its changes agree to follow. In relativity, the rule is written in the geometry that shapes your motion. In quantum theory, the rule is written in the phase that shapes your probabilities. And in your life, the meaning of a minute is written in what changes during it. So when you press your finger on the now and ask what it is made of, physics answers with a pair of voices, the traveler's proper time and the atoms, phase time, and the harmony you hear is not a contradiction but the sound of the same universe being honest at two different scales, inviting you to think of time less as a thing that flows and more as a story. You measure by comparing one steady transformation with another, a story that becomes simple when paths are clear and becomes rich when possibilities remain open. Atomic fountains and quantum seconds. You have probably never watched time arc through the air and fall back into a detector like a coin tossed in slow motion, but that is exactly what an atomic fountain does, and from this graceful toss, we squeeze out the most reliable seconds humans can make. The idea sounds like science fiction and feels strangely serene in practice. First, you gather a tiny cloud of atoms, often cesium or rubidium, inside an ultra-high vacuum chamber and cool them with laser light until they drift as if submerged in invisible honey. Then you nudge the whole cloud upward with a carefully tuned burst so the atoms rise, almost weightless, to the top of a narrow tower and then drift back down. And while they are mid-flight, you use a whisper of electromagnetic radiation to ask them a yes or no question that only the right frequency can answer. After which, you catch the atom's response in a gentle flash of fluorescence and convert it into a correction for your local oscillator, nudging your clock so that its beat matches the atom's natural rhythm. From this clean, quiet toss, launch, question, fall, answer, you carve a quantum second, a unit of time defined not by a planet's rotation, but by the internal rhythm of matter itself. The magic begins with cooling, because hot atoms zip around like toddlers in a playground, and their motion blurs every measurement. By shining laser beams from opposing directions, and keeping their color just off the atom's preferred absorption, you create what physicists poetically call optical molasses, where each atom is more likely to absorb light opposite its motion, and therefore slows down, step by step, until the cloud sits at micro-Kelvin temperatures, so cold that the atom's average speed is slower than a strolling insect. And this near stillness is essential because it reduces the Doppler effect that would otherwise smear the atomic resonance into a fuzzy hill instead of a sharp, climbable peak. Next comes the fountain's toss, and here the trick is simple and profound. By launching the atoms upward and letting them fly in free fall, you give yourself a long, quiet time window where the atoms are not bumping into walls or being jostled by forces, and a long interrogation time means a narrower line for the transition you care about. You can imagine it like listening for a pure pitch in a room after everyone else has left, and the longer you listen, the more certain you become about the note, which is why fountain clocks often stand a meter or so tall and repeat their toss roughly once per second. Each cycle a fresh attempt to hear the universe hum at exactly the same frequency as before. The question we ask mid-flight is encoded in an electromagnetic field tuned near the hyperfine transition of cesium or rubidium, two closely spaced energy states that differ in how the atom's nucleus and electron spins align, and the answer is beautifully binary. If the field is exactly right, the atom's internal state flips with high probability. If it is wrong by even a sliver, that probability drops. When the atoms fall back through a detection zone, we count how many flipped and how many did not. And that proportion tells us whether our interrogation frequency is a shade high or low, allowing a feedback loop to steer our local oscillator toward the sweet spot, where flips happen as expected, cycle after cycle. The phrase quantum seconds earns its name here, because when you lock your clock's beat to that transition, you are no longer relying on mechanical gears, spinning rotors, or celestial cycles that drift with weather and tides. You are referencing a fixed property of nature, the same in Paris and Tokyo, now and a century from now, and the international system of units defines the second by counting a specific number of these atomic beats, making time a universal contract written into matter. Precision. This extreme is not a matter of ceremony, but of hard, practical housekeeping. Many tiny shifts try to pull the atomic pitch off key, and the fountain's architecture is a crafted shield against them. Any stray magnetic fields can split the energy levels just enough to mimic a frequency error, so the chamber is wrapped in layers of mu metal shielding, and the average field is pinned to a known gentle value. The atoms themselves can collide and tug each other's frequencies, so you keep the cloud dilute or calibrate out the effect. Blackbody radiation from warm surfaces can nudge the transition, so you measure the chamber's temperature precisely and compensate. Even Earth's gravity is not uniform over a meter, so the atom's flight height is known to the millimeter, and the tiny redshift across that distance is accounted for in the final number. These details sound fussy until you realize what they buy. Fountain clocks now tick so steadily that if you started one at the dawn of recorded history and compared it to a twin today, they would disagree by less than a second, and that steadiness threads through your life in ways you rarely notice. From navigation satellites whose timing must align within billionths of a second, to the synchronization of communication networks, and the calibration of frequency standards that let laboratories trust each other across oceans. There is also a quiet artistry in how the fountain reads the atom's answer without disturbing them more than necessary, because every measurement risks shaking the system you are trying to keep still. The detection beam is tuned and shaped to tease out a crisp bit of fluorescence that betrays the atom's final state. And the electronics downstream are like a seasoned orchestra conductor, taking a stream of binary notes and turning it into a single, smooth command that shepherds the oscillator into alignment with nature's pulse. It is a conversation rather than a command, a gentle negotiation in which the atoms and the electronics teach each other to agree. If you are wondering why fountains became famous when their core frequency lives in the microwave region, while newer optical clocks boast even finer precision, the answer reveals a larger landscape. Fountain clocks perfected the art of slow, clean interrogation of atoms in free fall and set the modern baseline for timing. Optical clocks push the same idea to higher frequencies where each tick is shorter and therefore easier to count with greater granularity. But to turn those rapid optical beats into usable time, you need a frequency comb, an optical ruler that translates the buzzing of light into the rhythm electronics can follow. So in a sense, the fountain taught us how to listen to atoms in flight, and the optical revolution taught us how to translate a whisper from blue light into the language of circuits. Both live on the same principle that time can be defined by a stable quantum transition and measured by keeping everything else as quiet as humanly possible. The beauty of the fountain is that it turns gravity from an enemy into an ally. Instead of fighting weightlessness in an elaborate trap, you use the simple arc of a toss to create a long, interaction-free path. Then you ask your question twice, once on the way up and once on the way down, and the atoms themselves provide an interference pattern in the statistics of their answers that sharpens your ear for the correct note. The deeper mathematics of that two-step method deserves its own chapter, but here the message is that the fountain's choreography, cool, toss, question, catch, extracts a cleaner second than anything tied to mechanical motion ever could. And perhaps the most human part of the story is what this clarity does to your sense of time. It shows that a second is not a convenience we invented, but a truth we discovered, a steady drum in the heart of matter that we learn to hear by making the world around it very still. When you think of all the invisible labor behind your phone switching towers smoothly during a call or a plane, knowing exactly where it is over an ocean, remember that somewhere, in a quiet room, atoms are rising and falling like tiny coins in slow motion, answering the same soft question again and again. And from that patient conversation, your days, appointments, and journeys inherit their certainty, proving that sometimes the most intimate understanding of time comes from watching it fly. Ramsey Interferometry, ticking with phases. You learn most about a rhythm not by hammering it non-stop, but by listening to the silence between two gentle taps. And Ramsey Interferometry is the art of turning that silence into information, a way to let a quantum system keep time with its own inner phase, and then read it out with exquisite sensitivity. Imagine you prepare an atom, an ion, or even a superconducting qubit in a calm, well-defined starting state, and instead of blasting it with a long, continuous tone, you give it a brief, carefully shaped pulse that tips it into an equal blend of two internal possibilities. Think of it as a perfectly even split between this and that. And then you stop, you wait, and you let the system evolve on its own. Because during that quiet, the two possibilities accrue a relative phase. The way two hikers walking different paths around a hill return with different stories. And after a chosen pause, you apply a second pulse that tries to recombine those stories. If your external frequency is tuned so that your pulses are in step with the system's natural rhythm, the two halves meet as friends and the final state crowds into one outcome. But if you are even a touch off, the halves misalign and the result tilts the other way. And by scanning that detuning, you see a delicate pattern of bright and dark, fringes in the outcome probability, stripes, drawn not on a screen but in the statistics of many quiet trials that reveal the difference between your guess and nature's beat. What makes this method so powerful is that the useful information grows in the wait, not the push. The longer you allow that free evolution, the more phase accumulates between your split alternatives, and the narrower and more sensitive your fringe pattern becomes. A practical miracle that turns time into resolution. You learn to measure not by shouting at the system, but by timing the space between two whispers, which is why Ramsey's idea migrated from early molecular beams to trapped ions, cold atoms, solid-state defects, and even quantum processors, always carrying the same heartbeat: prepare, wait, recombine, while the hardware changes around it. On a conceptual globe of possibilities, the first pulse takes you from the North Pole to the equator. The free evolution is a smooth drift along the equator whose longitude encodes the phase, and the second pulse tries to bring you back to the pole. Whether you arrive at the North Pole or end up near the South is exquisitely sensitive to that longitude, which in turn depends on how closely your reference matches the system's internal frequency. This geometric intuition explains two crucial facts without equations. First, that the slope of the central fringe, the sensitivity, scales with the waiting time, because a longer glide along the equator turns a tiny frequency error into a larger angular shift. Second, that the method is both fast and gentle, since the system spends most of the sequence evolving freely with minimal disturbance. reducing the chance that your measurement itself spoils the very coherence you want to preserve. Of course, the silence is never perfectly silent. Stray magnetic fields tug the two internal possibilities differently and imprint an unwanted phase. Nearby light can shift the energy levels slightly. Collisions in a dense cloud nudge the rhythm, and even the microwave or optical pulses can introduce biases if their shapes are not exactly as assumed. Ramsey interferometry survives and thrives by acknowledging these imperfections and designing around them, averaging over field directions, shielding carefully, alternating interrogation settings to cancel offsets, and using clever variants like composite pulses or hyper-Ramsey sequences that deliberately add and subtract phase in a way that makes the true frequency stand out, while the spurious shifts cancel like debts. The elegance is that you are never trying to build a perfect world. You are trying to make a world in which errors wear name tags so you can subtract them honestly. In practice, you do not watch a single atom switch states once and declare victory. You repeat the two-tap dance many times, counting how often you land in one outcome versus the other, and a control loop rides the steepest part of the fringe, where a small drift in frequency causes a large, easily measured change in that count, steering your local oscillator into lock with the atom's private drum. This is how laboratory standards achieve their uncanny steadiness and how quantum sensors translate tiny influences, like a change in gravity across a centimeter or a whisper of a magnetic field, into measurable shifts of phase, because anything that changes the energy gap between the two states changes the phase accrued during the waiting time, and the Ramsey pattern dutifully slides to reveal it. The method teaches you a broader lesson about time. Phase is a kind of internal clock hand that keeps moving even when you look away, and the job of the scientist is to start it, step back, and then check where it points without grabbing the wheel. When you do this well, the system tells you not only what its natural frequency is, but also what touched it in the meantime, turning the quiet interval into a diary of the environment, written in winding angles rather than ink. It is tempting to think that you could always get more precision by waiting longer, but patience has an adversary called decoherence, the tendency of the environment to learn about which alternative the system took, washing out the crisp interference like mist blurring a mountain ridge. And Ramsey fringes fade when that happens. Part of the craft is choosing a waiting time that is long enough to build sensitivity, yet short enough to outrun the blur. And improving technology means pushing that boundary outward by cooling better, isolating more carefully, and designing sequences that refocus some of the wandering, like a traveler who pauses to look back and realign their bearings. Because Ramsey interferometry is not married to a single platform, it becomes a unifying language across fields, a pair of optical flashes interrogating an ultra-stable transition in a trapped ion, two microwave nudges addressing hyperfine states in a fountain of neutral atoms, a pair of radio frequency pulses probing the spin of a color center in diamond, even two carefully timed gates on a superconducting qubit. All of these are local dialects of the same grammar, where phase is the verb and interference is the sentence. And in each case, the outcome is not an abstract curve, but a control signal you can use to discipline an oscillator, calibrate a field, or sense a gradient, rooting lofty ideas in cables, cavities, and code. What you carry away, beyond the improved second and the sharper sensor, is a way of thinking. When you want to know a frequency, do not grip the system harder. Create a space where it can reveal itself. When you want to push sensitivity, invest in coherence, because clean phase is the currency of precision. And when you face an imperfect world, do not hide the imperfections under the rug. Weave them into your sequence so they cancel themselves. In the end, Ramsey's two taps are a reminder that knowledge often arrives between actions, that careful waiting can be as powerful as force, and that the deepest ticks in physics are not the clicks of gears, but the quiet turning of a phase hand. You can only see at the moment you choose to look, which is also a soft truth about your day. The clarity you seek shows up in the pauses you protect, and the better you listen there, the more exact your time becomes. The elegance is that you are never trying to build a perfect world. You are trying to make a world in which errors wear name tags so you can subtract them honestly. In practice, you do not watch a single atom switch states once and declare victory. You repeat the two-tap dance many times, counting how often you land in one outcome versus the other. And a control loop rides the steepest part of the fringe, where a small drift in frequency causes a large, easily measured change in that count, steering your local OSI later interlock with the atom's private drum. This is how laboratory standards achieve their uncanny steadiness, and how quantum sensors translate tiny influences, like a change in gravity across a centimeter, or a whisper of a magnetic field, into measurable shifts of phase. Because anything that changes the energy gap between the two states changes the phase accrued during the waiting time, and the Ramsey pattern dutifully slides to reveal it. The method teaches you a broader lesson about time. Phase is a kind of internal clock hand that keeps moving even when you look away. And the job of the scientist is to start it, step back, and then check where it points without grabbing the wheel. When you do this well, the system tells you not only what its natural frequency is, but also what touched it in the meantime, turning the quiet interval into a diary of the environment, written in winding angles rather than ink. It is tempting to think that you could always get more precision by waiting longer. But patience has an adversary called decoherence, the tendency of the environment to learn about which alternative the system took, washing out the crisp interference, like mist blurring a mountain ridge, and Ramsey fringes fade when that happens. Part of the craft is using a waiting time that is long enough to build sensitivity, yet short enough to outrun the blur. And improving technology means pushing that boundary outward by cooling better, isolating more carefully, and designing sequences that refocus some of the wandering, like a traveler who pauses to look back and realign their bearings. Because Ramsey interferometry is not married to a single platform, it becomes a unifying language across fields, a pair of optical flashes interrogating an ultra-stable transition in a trapped ion, two microwave nudges addressing hyperfine states in a fountain of neutral atom airs, a pair of radio frequency pulses probing the spin of a color center in diamond, even two carefully timed gates on a superconducting qubit. All of these are local dialects of the same grammar, where phase is the verb and interference is the sentence, and in each case, the outcome is not an abstract curve, but a control signal you can use to discipline an oscillator, calibrate a field, or sense a gradient, rooting lofty ideas in cables, cavities, and code. What you carry away, beyond the improved second and the sharper sensor, is a way of thinking. When you want to know a frequency, do not grip the system harder. Create a space where it can reveal itself. When you want to push sensitivity, invest in coherence, because clean phase is the currency of precision. And when you face an imperfect world, do not hide the imperfections under the rug. Weave them into your sequence so they cancel themselves. In the end, Ramsey's two taps are a reminder that knowledge often arrives between actions, that careful waiting can be as powerful as force, and that the deepest ticks in physics are not the clicks of gears, but the quiet turning of a phase hand you can only see at the moment you choose to look, which is also a soft truth about your day. The clarity you seek shows up in the pauses you protect, and the better you listen there, the more exact your time becomes. Quantum clock interference experiments. What if you could toss a clock into two different futures at once and then ask, when the halves meet again, whether it remembers which path it took? That is the strange promise of quantum clock interference experiments, where you split a single matter wave into two trajectories that feel slightly different histories, and then read the memory of those histories in the contrast of the pattern when the paths recombine, turning the act of keeping time into a test of how reality holds on to information. The basic stage is an interferometer built not from mirrors and metal, but from pulses of light that act like beam splitters and reflectors for atoms, sending one copy arcing a little higher or a little faster than its twin, so that each experiences a subtly different rate of ticking because of motion or gravity. And inside each atom, a quiet hand, the relative phase between two internal energy states, advances like the second hand on a private dial, so that when the twins reunite, their internal hands may point to slightly different angles, and that difference can either preserve the beautiful interference fringes or wash them away, depending on whether the two internal clocks still agree. If the hands remain aligned, the two histories are indistinguishable, and the interferometer paints sharp stripes, But if the hands drift far enough apart to tell the paths apart, the stripes fade, as if the universe had whispered, "I know which route you took." A whisper that costs you the interference you were hoping to see. The practical choreography is delicate but graspable. A cloud of atoms, prepared with care so their motion is calm and their internal state well-defined, is struck by a first pulse of laser light that imparts momentum to one branch but not the other. So the wave splits into two lobes that fly apart like twins in a controlled disagreement. Along the way, you can nudge only one branch with an additional bit of electromagnetic radiation so that its internal dial begins to tick at a slightly different pace. Or you can simply let gravity do the job by sending the two branches through different heights, where time flows at different rates, and then a second sequence of light pulses steers the copies back together. At the final screen, you do not watch a single atom, but count many outcomes, and the rise and fall of those counts as you scan a control parameter draws the familiar interference pattern, a map of coherence that now carries the story of a clock. What makes these experiments more than clever gadgetry is that they let you separate two roles time plays, as geometry, which tells each path how long its journey is, and as information, which can tag a history in a way that destroys superposition. By adjusting how quickly the internal dial turns, choosing different atomic transitions to act as a clock, or adding controlled perturbations, you can tune whether the clock is sensitive enough to record a which path mark, and then you can go a step further and deliberately erase that mark by rewinding or refacing the internal dial before recombination, restoring the lost fringes and proving that it was the availability of path information, not some crude disturbance that ruined your pattern. There is something almost tender about watching visibility vanish when the clock learns too much, and then return when you make it forget. In the background, a profound question is being tested with concrete data. Does a quantum object in a superposition of altitudes tick ambiguously in a way that matches our best understanding of gravity's effect on rates? And is that ticking itself enough to cause loss of coherence? You do not need equations to appreciate the intuition. Higher paths age a touch faster than lower ones because the pull there is weaker, and faster paths age a touch slower than slower ones because motion saps aging. And a quantum interferometer, by letting one copy age differently from its partner, translates these tiny differences into a measurable change in pattern contrast, a kind of chronometric seismograph that registers attoseconds of disagreement by shifting the brightness of stripes. By confirming that the loss of interference tracks the distinguishability carried by the clock, these studies tie together two pillars that usually live in separate chapters, showing that the rules for time in gravity and the rules for information in quantum theory can be made to speak the same language at the laboratory scale. Experimentalists have learned to make that conversation crisp by trimming away every noisy accent. They shield stray magnetic fields that would twist the internal dial unpredictably. They keep the atomic density low enough to avoid collisions that would smear the hands. They measure ambient temperature, so thermal light does not nudge the transition off pitch. And they design pulse sequences that cancel biases by symmetry, so that what remains is the clean effect of path-dependent ticking. Sometimes the two branches are separated by millimeters, sometimes by mere micrometers. But the principle holds. The more the internal hands disagree at the moment of reunion, the less willing the two copies are to create a bright pattern together. A lovely twist is that the clock does not have to be fast to be useful. Even a slow internal rhythm can be made decisive if you let the branches stay apart long enough, or if you choose a geometry that exaggerates the difference in their experiences, which is why the same concept has appeared in neutral atom interferometers, trapped ion architectures, and even schemes with molecules whose rich internal structure provides many candidate dials. Across platforms, the shared lesson is that phase is both a measure of time and a carrier of knowledge. And the tug of war between precision and privacy, how much the system reveals about its root, is what sets the limit on the patterns you can coax from it. This is not just physics for its own sake. When you take the pulse sequence that controls the splitting and recombination and convert it into a sensor, the device becomes a tool for measuring gravity gradients, rotations, and tiny accelerations with startling sensitivity. Because anything that changes the relative ticking along the two paths slides the interference pattern in a way you can track. turning the lab into a kind of time microscope for the environment, a technology with obvious reach into navigation, subterranean mapping, and tests of foundational principles like whether all forms of energy fall the same way. The fact that a philosophical idea about clocks in superposition yields a brick and cable instrument that can find a buried void or way. The pull of a mountain slope is one of those quiet triumphs that makes science feel both humble and grand, and yet the softest lesson might be personal. A quantum clock that learns too much about where it has been loses the ability to interfere with its other self, and only by letting go of that knowledge, by arranging the erase that brings the hands back together, does the full pattern return. You can hear in that a gentle reminder that there are kinds of remembering that isolate you and kinds of forgetting that make you whole. That sometimes the most precise understanding comes not from holding every detail, but from designing the right reunion. And that in a world where even time can be made to carry a label, you keep your curiosity honest by asking your questions so carefully that nature can still choose to answer in a chorus. In the end, watching a clock interfere with itself teaches you that time is not only what you count, but what you can unknow. And the picture that remains, bright, dim, bright, feels like a human heartbeat laid over the quiet machinery of the universe. Gravitational redshift of quantum clocks. You would not expect moving a clock from the floor to a chair to change anything about what a second means. Yet gravity makes that tiny lift matter, and quantum clocks are now sharp enough to hear it. The gravitational redshift is the plain statement that time itself runs at different rates at different heights in a gravitational field. Deeper runs a little slower, higher runs a little faster. And while this was once a story about photons climbing out of a star and arriving stretched, today it is something you can verify in a quiet lab by comparing two identical quantum clocks placed at slightly different elevations and watching their ticks drift apart by a minuscule but measurable amount. The key is that a modern clock's tick is set not by a gear or a pendulum, but by a jump between two well-chosen energy states in an atom or ion. A transition so regular that its frequency is the same in every laboratory on Earth. And when the clock sits lower in Earth's gravitational potential, that frequency is shifted just enough that, over time, it falls behind its twin sitting a bit higher, exactly the way relativity predicts, turning altitude into a value you can read in hertz rather than meters. To make this concrete without drowning in symbols, picture two strontium lattice clocks, trillions of neutral atoms held in place by a standing wave of light that forms a kind of egg carton for matter, parked on two shelves a few centimeters apart. Each clock uses ultra-stable laser light tuned to a particular optical transition and a frequency comb to count those rapid beats in the language of electronics. And each clock is guarded from every mundane nudge. Stray magnetic fields are tamed. The surrounding temperature is known and corrected because warm walls shift the tick slightly. The atoms are cooled to near a standstill so motion does not blur the line. And the trapping light is chosen so it does not favor one state over the other. When you compare the two, the higher clock's beat is faster by roughly 1 part in a billion per centimeter of height, a fraction so small that it takes the stability and purity of quantum references to see it at all. But it is there, steady as sunrise, and it matches the simple expectation that being closer to the planet's mass slows your rate just a touch. This is not merely a laboratory curiosity, it is the seed of a new kind of mapping called chronometric leveling, where you use clocks to survey gravitational potential the way a carpenter uses a spirit level, and with fiber links that carry stable light between sites, or free space optical links that bridge longer gaps. National labs can now compare distant clocks and turn frequency differences into height differences, with a sensitivity far beyond classical surveying over long baselines. Which means you can watch tides in Earth's crust, track how groundwater redistributes mass beneath a region, or monitor the slow settling of land around a city by listening to time rather than peering at a ruler. The quantum in quantum clock here matters because the transition you interrogate is a clean, microscopic standard that does not care about where or whether, and its isolation from noise is what lets you resolve the redshift across the height of a small book. In some experiments, researchers have even resolved the effect within a single trapped cloud of atoms by comparing slices separated by less than the thickness of a fingernail, revealing a tiny gradient in tick rate across the sample itself, a kind of internal topography of time that would have been science fiction a generation ago. And in single-ion clocks, where one carefully chosen ion is suspended and read out with exceptional precision, the same principle holds, though the geometry and noise sources differ, and comparing different species against each other provides not only a redshift check, but also a probe of whether fundamental constants drift over years, which would hint at new physics. The care that goes into an honest redshift measurement teaches you what can fake the effect and how to avoid being fooled. Temperature shifts from the apparatus can push the frequency. Electric fields from the trap or the lattice light can distort levels, and even small magnetic field inhomogeneities can tug the transition off center. So the measurements are done with reversals and interleaved settings that cancel biases, with redundant sensors, with alternating polarizations of light, and with long averaging times that turn random noise into a harmless blur until the only remaining, consistent difference between the clocks is their position in Earth's potential. That discipline turns a delicate prediction of general relativity into a practical yardstick you can trust. What makes this story feel fresh is that it bridges two intuitions you carry separately. One about gravity bending paths and slowing rates, another about quantum matter providing perfect ticks. When an optical clock climbs a few stairs and you watch its frequency quicken ever so slightly, you are watching geometry feed directly into a quantum phase advance. And that unity is not poetic dressing, but the operational way your world works. Space-time tells the clock how to run, and the clock tells you where you are in space-time. There are, of course, frontiers inside this frontier. How small can the separation be and still yield a clean, local redshift you can resolve? Can you turn a lattice of many microscopic clocks into a camera for gravitational potential that images variations across a room? Could portable, battery-powered optical clocks make regional gravity maps in the field for volcanic monitoring or resource surveys? All of these directions build on the same seed, time sensitivity to height, and all depend on continuing to tame noise, shrink size, and simplify the complex optical plumbing that currently fills a table. Meanwhile, the implications circle back to tests of first principles. Every time a redshift measurement agrees with the expected potential difference, you reaffirm a pillar called local position invariance, the idea that the laws of physics do not secretly depend on where you are. And by repeating such tests with different types of clocks, at different frequencies across seasons and places, you both reinforce relativity and open small windows through which new physics would be visible if nature deviates in the 12th decimal place. The quiet thrill is that your instrument for probing such lofty questions is a device that counts light's heartbeat and notices when lifting it. The height of your hand changes the count by a whisper, and there is a gentle personal moral hidden in the engineering. You learn that where you are shapes how your time passes, not in a mystical sense, but in a direct, measurable way, and you discover that precision is a way of seeing, cleaning up your environment, removing distractions, and comparing carefully until a pattern appears. After spending time with these clocks, it becomes hard not to feel that your days, too, are shaped by the potentials you choose to live in, that climbing even a small step, literal or figurative, can change the pace of what you notice, and that sometimes the deepest insight into a grand theory arrives the moment you realize a half-inch of elevation is enough to make time itself draw a new line in the sand. Time, energy, uncertainty, carefully explained. Start a stopwatch and ask an atom a simple question. What note are you singing? And you'll discover that the more patiently you listen, the clearer the pitch becomes. Rush the measurement and the tone smears into a blur, not because nature is hiding answers from you, but because the very act of resolving a frequency demands time. This is the honest core of the time-energy story, often dressed up with dramatic claims about borrowing energy from the vacuum. Yet in reality, it is quieter, cleaner, and more interesting. Energy is a measure of how fast a quantum state's phase twists, and time is the stage on which you allow that twist to reveal its rhythm. So the less stage you grant, the more ambiguous the rhythm sounds to your instruments. To understand it without symbols, imagine two versions of the world. In one, A system sits in a perfect, unchanging note, what physicists call a stationary state. And if you could listen forever, its pitch would narrow to a razor line because nothing in it evolves except a hidden internal clock. In the other, the system changes because you disturbed it, or because it naturally decays, and that changing tone can never be pinned to a single frequency. The way a bell struck lightly sings a pure ring if you let it fade. But a bell you keep tapping refuses to settle. Time and energy are not a pair of objects you hold in two hands like position and momentum. They are a relationship between evolution and the effort needed to resolve it. Here's the first core idea, kept painfully accurate. There is no universal time operator in standard quantum mechanics, like there is a position operator. So the everyday uncertainty rule you may have heard for position and momentum does not simply copy-paste to time and energy. Instead, the relevant statement is about how sharply you can define energy given how long you look, and how quickly a state can change given the spread of energies it contains. These are two different but related lenses on the same reality. The measurement lens is intuitive. To say, this atom's energy equals that, you do not grab a chunk of energy, you let the atom's internal rhythm beat against a reference and watch the interference. If you watch briefly, the beats cannot tell you a precise pitch, just as a musician cannot identify the exact note of a 1 millisecond blip. Stretch your observation, and the spectral line narrows. This is why spectrometers that stare longer resolve finer features, and why the best atomic clocks dwell on transitions for long interrogation times. Time becomes resolution. The dynamical lens is equally honest. If a state is a mixture of different energy notes, those notes interfere to produce changes you can actually see, so a wider mixture can generate faster evolution. In plain terms, a system with a broad energy palette has more rhythms to combine and can move to a noticeably different configuration in less time, while a state concentrated near a single energy changes slowly. That is why there are rigorous speed limits on how quickly a quantum system can rotate from what it is to something measurably different, bounds that connect the pace of change to the energy landscape without invoking mystical shortcuts. Now consider unstable systems, the workhorses of real laboratories. An excited atom that emits light, a short-lived particle that decays, a resonant molecule that sheds energy into its surroundings. Because these states do not last forever, their note is not infinitely sharp. The result is a line of finite width in a spectrum, a practical fingerprint of the fact that the probability of survival falls over time. Lifetime and line width are two sides of the same coin, and any laser builder or astrophysicist reading spectral lines from a star relies on this trade-off without once imagining that conservation of energy is being violated. Energy accounting remains exact in the full system. Atom plus field, particle plus decay products. What broadens is your ability to assign a single, perfect number to a transient drumbeat. This is the moment to puncture the most viral myth. When popular accounts say, a particle borrows energy for a short time as long as it pays it back quickly, they are using a metaphor that easily misleads. Nothing in nature opens a cosmic credit card. What actually happens is that processes too brief to isolate a single frequency necessarily involve a range of energy components in the mathematical description. And when you compute probabilities for outcomes, you always find exact conservation in what is observed. The story about borrowing is a sloppy cartoon of how intermediate calculations are organized, not a license for energy to appear and vanish. You can test your intuition with ordinary experiences. Tune a radio quickly across a station and you hear a smear. Park on the station for longer and the song clarifies. Try to identify a singer from a 1-second clip and you guess. Give yourself a full verse and you know. Take a long exposure photo and you reveal faint, precise features. Take a rapid snapshot and you catch motion but lose fine detail. In each case, time is the lever that trades off immediacy against precision. Spectroscopy, clock building, and even the analysis of seismic waves follow the same logic. Not because engineers conspired to make it so, but because the mathematics of waves, any waves, binds frequency resolution to observation duration. If you want a concrete, curiosity-friendly example that matters in the lab, look at the width of sodium's famous doublet. Lines in a street lamp or the razor-thin transitions in optical, lattice clocks that now keep time so steadily, they would drift by less than a second over the age of the universe. The trick that makes those clocks stunning is slowing everything down in the right way, cooling atoms, trapping them, reducing environmental noise. So the system behaves almost like a perfect stationary note, and then interrogating that note for as long as possible. The reward for patience is a frequency measurement with extraordinary certainty. If you cut the interrogation time, the peak in your readout fattens and your certainty erodes. The same trade-off shows up at the opposite extreme. Ultra-fast science uses very short pulses of light to chase rapid dynamics in molecules and materials, accepting that the pulses must carry a wide range of colors because you cannot have a pulse that is both extremely brief and extremely monochromatic. Here, the breadth of energies is a tool rather than a nuisance, because broad spectra can trigger and probe rapid changes. In both slow and steady metrology and fast and furious dynamics, the time-energy relationship is not a limitation imposed by a grumpy universe, but a map telling you what is possible with the resources you invest. Notice how this perspective keeps you away from needless mysticism. There is no general law forbidding you from knowing energy and time at once, because time is not a property the system possesses in the same way as position. Instead, there are clear statements about how long you must watch to resolve energy, and how the spread of energies in a state bounds how quickly that state can transform. Blend those statements with careful experimental design, and you choose where to live on the continuum from sharp energy, slow knowledge, to blurry energy, fast snapshots. This clarity also guards you against hype. When you hear that short-lived particles have fuzzy masses, recognize that fuzzy means the resonance peak in a detector has a width set by the particle's lifetime. When you hear that virtual processes violate energy conservation, remember that real, measurable outcomes never do. What is uncertain is not the bookkeeping of nature, but your ability to assign a perfect single number to a process you did not allow to sing long enough. So the next time someone sells you the drama of time-energy uncertainty as a cosmic loophole, you can smile and explain the calmer truth. Energy is the rhythm of a quantum state. Time is how long you let that rhythm play. The more patient you are, the more precisely you can name the note, and the less patient you are, the richer the chord you must accept. Either way, the music remains perfectly accounted for, and your job, beautifully scientific and deeply human, is to choose how you want to listen. Quantum speed limits. How fast can states change? Imagine you could pin a tiny speedometer not on a moving car, but on change itself. How fast a quantum thing can become something measurably different. And you'd find a surprising rulebook. Even with unlimited cleverness, there is a hard floor on the time it takes for a state to transform. A built-in no faster than this that doesn't come from the speed of light, but from the way quantum rhythms add up. This is the story of quantum speed limits, not science fiction loopholes or motivational slogans, but sober boundaries that tell you the minimum duration required for a system to evolve from here to decisively not here. The cleanest way to feel it without equations is to picture a point on a sphere, the Bloch sphere if you like, where every direction stands for a different configuration of a simple quantum bit. When you drive that point with a control field, it traces a path across the surface, and if your goal is to flip it to the opposite side, turning a definite this into a definite that, there is a shortest possible arc and a fastest possible pace, determined by the energy resources you've committed. The broader the range of energies present in the state during the journey, or the higher the average energy you inject above the system's baseline, the quicker the point can sweep across. Starve it of energy variety, or keep it near idle, and the motion crawls, no matter how fancy your steering. The first great insight is that distance between quantum states isn't about centimeters. It's about distinguishability, the angle between two notes played by the system. So going from a state to an exactly orthogonal one is like turning a musical phrase into something no ear could mistake for the original. The speed limit says there is a minimum time for that rotation. And if your target is only partially different, say, distinguishable with 90% confidence instead of 100%, the minimum time shrinks in a precise way. In other words, nature prices how far you want to move in units of change you can actually detect. The second insight is that these limits come in two complementary flavors that speak plain language. One says your pace is tethered to how much the state's internal energies are spread out. The more diverse the frequencies you let the system carry, the faster the interference of those frequencies can steer it into a new shape. The other says your pace is tethered to how much energy you keep on average above the ground. The more fuel you load relative to idling, the faster the engine can rotate the state. You can't cheat by fancy choreography because the limit is geometric. The shortest path at the maximum safe speed, and you can at best saturate it with the perfect drive rather than break it. This is not a philosopher's toy. It shows up whenever you ask a concrete, practical question like, how quickly can I flip a qubit without errors overwhelming me? Or, what is the shortest pulse that still achieves a reliable population transfer in an atom? A resonant pi pulse that flips a spin in nuclear magnetic resonance is a textbook illustration. Make the pulse stronger and the flip gets faster, but there is a point where you are skimming the ultimate boundary for the allowed energy and path. Push beyond the model's assumptions, and you leak into unwanted states or fry the sample, not because the universe is mean, but because the geometry of change itself pushes back. Quantum computing lives inside this vice, squeezed between two walls. On one side, decoherence waits, ready to scramble your carefully prepared states if you dawdle. On the other, the speed limit forbids you from compressing logic operations below a certain duration for the energy you can safely apply. The art of good hardware is to raise the ceiling, shorten the path, and hush the environment so your moves remain coherent long enough to finish the dance. When you see a headline boasting record-fast 2-qubit gates in superconducting circuits or trapped ions, this is what they are optimizing, staying as close as possible to the limit while keeping errors tame. The same trade-off guides ultra-fast chemistry and materials science. To watch an electron jump across a molecule or through a semiconductor, you excite it with a short burst of light. But a pulse that is extremely brief must contain a wide range of colors, which is exactly the broad energy palette that enables rapid change. The speed limit is not an annoyance here, it's the playbook. If you want to trigger a transformation in femtoseconds, you must embrace the spectral width that can drive it, then shape that width so it goes where you intend instead of splashing into side reactions. Coherent control and shaped pulses are essentially cartography on this landscape, drawing efficient routes that kiss the limit without overshooting. Even the dream of shortcuts to adiabaticity, where you try to get the benefits of slow, careful evolution in a fraction of the time, must pay the bill. Yes, extra control fields can cancel unwanted excitations and keep the system on track. But the extra fields carry energy and complexity, and once you account for realistic bounds on control strength and bandwidth, a speed limit remains. Some costs cannot be magicked away, only moved around. In the growing field of quantum thermodynamics, these limits become the tempo markings for microscopic engines and refrigerators. You cannot expand and compress a quantum working medium arbitrarily quickly while keeping it in good order. Go too fast, and you generate friction-like excitations that lower efficiency. Go too slow and you lose power. Between these extremes sits an optimal cycle time that balances change against coherence, and the speed limit helps you find it without hand-waving. This is also why proposals for quantum batteries talk about charging power rather than just stored energy. Interactions and entanglement can give you collective advantages, letting many cells charge in parallel more effectively than one by one. But the overall charging time cannot drop below the bound set by the available interaction energy, and the distance in state space you must cross to reach a fully charged configuration. Noise complicates the picture, but doesn't erase the wall. In open systems where the environment pokes its nose into the dynamics, the fastest track to a target state is often slower because some of your carefully arranged interference is being smeared out. In rare cases where the environment has memory, well-timed couplings can briefly recycle coherence and effectively speed parts of the journey. Yet revised speed limits exist for these situations too, guarding against wishful thinking and loose metaphors about teleporting change. If you want a hands-on feel, think like an engineer. Say you must rotate a spin by a certain angle with a specified error budget, and your lab hardware caps the maximum field you can apply. The limit tells you the best case gate time, even if you had perfect software and zero latency. So you can decide whether the device's coherence is long enough for the job. Or imagine a molecule whose electrons need to move from a donor site to an acceptor before energy leaks away to heat. The limit gives you a target pulse duration and spectral width needed to outpace the lost channels. This is design, not dogma. And because the limit is geometric, it unifies diverse tasks. State transfer along a chain, entanglement generation between distant qubits, phase imprinting in an interferometer. even distinguishing two nearby hypotheses about a system's identity in metrology. The minimal time to achieve a desired distance under a cap on energy resources appears again and again, the same melody in different keys. It's worth also puncturing a pair of common myths. First, quantum speed limits are not the same thing as the time it takes a particle to cross a spatial region, so all the old paradoxes about tunneling time live in a different neighborhood. Second, these limits are not vague philosophical statements about uncertainty in general, but precise, testable inequalities that have been saturated in carefully engineered experiments. Fast spin flips, rapid Landau-Zener sweeps, and strong drive Rabi rotations come close to the bound when the drive is resonant and well controlled. The deeper message, and the one that matters for how you think about possibility, is that speed in the quantum world is a resource you budget like money or time in your own life. You can trade average energy for a quicker route, or trade spectral breadth for flexibility, but you cannot get something for nothing. The universe will let you dance brilliantly on the edge if you bring the right music and keep your steps clean. Yet it will not let you skip beats. So when you hear the phrase, "How fast can a quantum state change?" you don't imagine a vague, mystic fog. Imagine a crisp map with the shortest road marked in bright ink, a speed limit posted in plain numbers you may not see but your apparatus can feel, and a set of levers you can pull: control strength, bandwidth, pulse shape, interaction design, to get as close as physics allows. Push harder and you waste effort or create heat. Back off and you miss your window. But ride the line and you discover something quietly thrilling. Beneath the strangeness, the quantum world is disciplined about time, and that discipline is exactly what lets us build clocks, computers, sensors, and engines that work not by breaking the rules, but by meeting them with elegance. Quantum coherence as a time resource. You don't usually think of silence as something you can spend, yet in quantum physics the most valuable thing you can hold on to is a kind of organized quiet, the delicate phase relationship that lets a system keep its own counsel for a while. And that organized quiet is what we call coherence, a resource you can save, waste, invest, or convert. And when you treat it that way, time itself becomes something you can measure, trade, and shape with surprising finesse. To see why, imagine preparing many identical quantum arrows that all point in step in an abstract direction you can't see with your eyes, and then letting them evolve. If their phases stay lined up, their joint rhythm tells you how long they have been left alone, much as a tuning fork's ring fades but keeps pitch long enough to serve as a reference. Whereas if each arrow talks to the environment and loses track of the others, the chorus turns into a hiss, and the system forgets how to tell time. Coherence is precisely that alignment in phase, and it converts the passage of time into a measurable change without blur, which is why laboratories go to absurd lengths to chill, shield, and isolate anything they want to use as a timer or a sensor. Once you accept coherence as a resource, a practical map appears. You can store it in well-chosen systems. You can move it between degrees of freedom. You can distill it from many mediocre copies into a few excellent ones. And you can spend it to buy precision or speed. Think of a spin in a magnetic field, precessing like a microscopic compass needle. While its phase remains sharp, its angle is a faithful clock hand. But every random nudge from the outside world smears that angle and converts your expensive clarity into cheap heat. So experimentalists fight back with tricks that are really financial moves in disguise, such as echo sequences that pay a small amount of control effort now to recover coherence later by unwinding certain errors, or pulse trains that hedge against slow drifts by flipping the system so that what one interval takes away, the next interval gives back, extending the time window over which the phase remains readable. Each of these methods lengthens the coherence time, not by magic, but by redirecting how the system exchanges information with its surroundings, pushing uncontrollable noise into directions that no longer matter for the quantity you care about. The idea reaches beyond a single qubit or atom when you consider shared references. A laser is valuable not just because it is bright, but because its phase is coherent over long intervals, meaning it acts like a communal metronome that different labs can lock to and then compare across continents through optical fibers or precisely steered beams, turning individual clocks into a network that can agree on time to absurd accuracy. Coherence here is clearly currency. You use the laser's phase order to purchase agreement among distant devices. And you can even audit how well you did by looking at the residual wander in their difference signal. There is also a striking, less obvious conversion you can perform. Under certain controlled rules, you can trade coherence for work and back again, like exchanging cash and credit, a point explored in modern quantum thermodynamics, where the usefulness of a state includes not only how much ordered energy it carries, but also how much phase order it holds relative to a chosen reference. While the detailed bookkeeping is technical, the lesson is human-readable. If you start with a system that has clean phase order relative to your clock, you can arrange interactions that extract more purposeful change than a sloppy, incoherent state could deliver. And conversely, any irreversible process that lets the environment learn which way your phase pointed will reduce the future work you can hope to extract, because the world has already cashed in your coherence as entropy. Treating coherence as a budget also explains why some daring proposals for quantum technologies succeed only when you pair them with a realistic account of noise. For example, you can boost timing sensitivity by preparing many particles in a special, highly coordinated state whose phase responds more strongly than a crowd of independent ones. But that leveraged sensitivity is fragile. Every bit of uncontrolled chatter from the environment erases your advantage faster than it erases ordinary coherence, much as a risky investment amplifies both gains and losses. The frontier is learning how to engineer surroundings that are quiet in the specific ways that matter most, and how to encode information in patterns that are inherently less vulnerable to the kinds of errors your hardware can't avoid. Everyday technologies already depend on this calculus, even if they don't advertise it. Medical imaging machines listen for coherent precession of nuclear spins and tame dephasing with carefully timed pulses, so the signal survives long enough to be mapped into an image. Gravimeters and inertial sensors translate tiny changes in motion into phase shifts and therefore guard coherence with vacuum chambers, low vibration mounts, and low noise electronics. Quantum communication schemes send coherence down fibers as fragile packets of phase, and network designers sprinkle in repeaters and error correction to keep that phase legible after kilometers of glass and rain. Perhaps the most empowering part of this resource view is that it tells you how to plan. Before you ask for precision, you ask where the coherence will live and for how long. Before you promise speed, you count how much phase order you can afford to burn to reach a target in the allotted time. Before you link many devices, you decide what shared reference will carry the phase discipline across the network. And when a result underperforms, you do not reach for mystical explanations. You open the ledger and look for where the coherence leaked, then decide whether to plug the hole, reroute the flow, or redesign the task so the remaining budget is enough. If there is a soft lesson to carry beyond the lab, it is this. Coherence teaches that clarity is not merely the absence of noise, but the presence of alignment, something you build, protect, and sometimes regain with clever echoes after a stumble. In physics, that alignment lets matter tell steady time. In life, it shows up when your actions, attention, and goals pull in the same direction long enough for change to become measurable. Either way, you learn not to confuse intensity with order. Shouting at a system does not make it a better clock, and you begin to respect the quiet intervals you protect on purpose, because that is where phases line up, signals add instead of cancel, and moments become legible against the blur. Clock synchronization, the quantum way. You cannot run a civilization on scattered minutes. So the quiet miracle behind modern life is that far-flung clocks agree well enough for planes to land, stock trades to settle, and telescopes on different continents to behave like one giant eye. And the quantum way to synchronize them begins with a simple promise. Instead of sending chunky timestamps and guessing how much the path delayed them, you share the very rhythm of matter and light. Compare phases directly, and use correlations that only quantum physics can provide to cancel the path's tricks. Start by picturing two labs that want to breathe in the same tempo, one on your rooftop and one across a city, or even across a country, each guarding an ultra-stable oscillator, each listening to an exquisitely narrow transition in atoms or ions, and each linked by a channel that stretches through fiber or free space. The classical approach is to send ticks back and forth and average the round trip, which works but always leaves a little doubt, because the route to you may not match the route back, and the air, glass, temperature, and motion all play games with delay, while the quantum approach treats time not as a number you ship, but as a phase you share. so the two ends lock to a common carrier that both see in nearly the same way, cutting away much of what used to be guesswork. The beating heart of this is phase-coherent light, and the ability to count optical cycles you cannot see with your eye, a frequency comb, a light source whose colors form a regular ruler, lets each lab translate an optical rhythm into radio beats that electronics can count. And if you send that optical rhythm across a stabilized link while also sending a return signal, you can measure and cancel the path's wander in real time, leaving behind a copy of the remote clock's phase that rides into your lab as if the distance had evaporated. When the link must cross the open air, you point small telescopes at each other and use two-way exchange to subtract turbulence. And when the link must cross a continent, you borrow dark fibers in the telecom web and actively push against temperature drifts and mechanical stress, so the phase at your end still mirrors the phase at the other. The quantum edge shows up in two ways your intuition can hold. First, you use non-classical correlations, pairs of photons whose detection times are linked more tightly than any classical pulse train, to compare clocks without relying on a perfect knowledge of the path, because coincidence timing between the two labs can be sharpened by the physics of the pair itself. Second, you can distribute entanglement between distant nodes and make the shared state act like a reference that is everywhere at once, so that measuring your half tells you how to nudge your clock even before any classical message arrives. With the final agreement confirmed when the ordinary signals catch up, you do not break causality by doing this. You simply move some of the heavy lifting into correlations that do not care about individual delays, which makes the whole network less fragile to asymmetric routes and less open to adversaries who try to spoof timing with clever replay tricks. In practice, you build trust by redundancy. You still do two-way exchange to remove path delay, but you also compare the phase of light that never left the building with the phase that went out and came back. You cross-check microwave beats against optical ones via the frequency comb, and you route signals along separate fibers or separate air paths so that local disturbances reveal themselves as disagreements. When the pieces harmonize, the two clocks sit on the same tick within billionths or trillionths of a second over long periods, a level of agreement that turns arrays of radio dishes into one coherent telescope, allows navigation systems to triangulate with confidence, and lets distant laboratories compare fundamental constants without being tricked by their plumbing. There is a subtlety you must respect. Synchronization is not the same as declaring two events simultaneous, because at high precision you must honor relativity, moving platforms, Earth's rotation, altitude differences, and gravitational potential shifts all tweak rates and phases. So a quantum-aware network carries along a quiet layer of space-time bookkeeping. Receivers know their motion, correct for Sagnac effects on spinning Earth, adjust for height so that redshift does not creep in, and keep a running ledger so that when a packet of phase arrives, it is folded into a model of the world that is honest about geometry as well as electronics. Beyond the backbone, quantum tricks help at the edges. You can use interference that only occurs when two independent lasers are truly in step to validate that your local light is phase-locked to the remote master. You can send time-bin encoded photons whose early-late structure is robust against many forms of noise, making them good couriers of timing over dirty channels. You can tap Hong-Ou-Mandel interference, the tendency of identical photons to coalesce into the same output, to line up remote pulse trains with femtosecond sensitivity, because the dip in coincidence counts marks the moment two wave packets truly overlap. Each method converts a fragile path into a sharp reference event that both ends can recognize without trusting the path's story about how long it took to get there. Security, too, is different when you lean on quantum features. Because certain correlations cannot be forged by classical means, you can detect attempts to tamper with timing, much as quantum key distribution detects eavesdropping. And while the network still needs good engineering, calibrated delays, authenticated control signals, and stable hardware, the physics itself becomes an ally, raising the cost of deception. The payoff of treating synchronization as shared phase rather than traded timestamps is that you can build clock networks that scale like instruments, not like compromises. You stitch together optical clocks in multiple countries, so they act as a single reference for redefining the second. You compare frequency standards fast enough to catch subtle drifts in value, opening tests of whether nature's constants truly stay constant. You coordinate arrays of quantum sensors to listen for faint ripples in gravity or subtle shifts in Earth's mass distribution, extracting common mode noise and summing useful signal across the whole network, the way a choir projects farther than a single voice. And there is a soft lesson tucked inside the cables. Real agreement comes not from shouting the time at each other, but from sharing a rhythm and correcting for what the world does to it along the way. In the lab, that means phase locks, two-way links, and correlations that lay bare the path's mischief. In your life, it might simply mean choosing references you trust, exchanging signals in both directions, and keeping a clean ledger of the forces that tug your days fast or slow. Either way, the quantum way to keep time together teaches you to synchronize by listening as much as speaking, to measure the channel as carefully as the clocks, and to build unity out of shared structure rather than fragile broadcasts, so that when you and someone far away look up and say "now," the word lands, with the kind of quiet confidence that makes everything else possible. Quantum metrology, beating classical timing. You've been told that patience and averaging beat noise, that if you count long enough the truth emerges. But quantum metrology offers a bolder deal. Instead of waiting longer, you can listen smarter by shaping the very fluctuations that limit you, and by arranging particles to act not like strangers, but like a choir that sings in tune. So your estimate of time improves faster than any classical strategy could allow. The classical rule of thumb says that if you have n independent ticks, photons in a pulse train, atoms in a cloud, electrons crossing a junction, your timing uncertainty shrinks only as 1 over the square root of n, which is why traditional instruments demand more power or more minutes to gain another digit. Yet quantum tools change the slope of that climb by reorganizing randomness itself. You squeeze noise away from the variable you care about, and you introduce correlations, sometimes even entanglement, so that the signal grows like n, while the relevant noise grows more slowly than the old square root law, letting the same number of particles in the same time tell you more. To feel this without equations, think of a crowd counting seconds aloud. If each person is free to wobble, the average improves slowly. But if you teach them to lean in a coordinated way that makes early or late errors cancel in the dimension you measure, the group can mark time with a crispness no solo counter could match. In the lab, that coordination takes many forms, each with a distinct personality. Light can be prepared in a squeezed state where the arrival time jitter you read out is reduced at the price of extra uncertainty hidden in a complementary property you do not measure, and that stolen jitter translates directly into sharper timing. This is not a metaphor, but a practical upgrade already used to sharpen interferometers that listen for feeble ripples in space-time. Atomic ensembles can be spin-squeezed by letting a probe beam learn just enough about their collective orientation to reduce the spread of the readout you care about while pushing the unavoidable disturbance into a direction that does not spoil your clock. And the result is a thinner distribution of outcomes around the true phase advance you want to track, giving you better digits per unit time. And in the most dramatic version, specially crafted many-particle states behave like a single, giant hand that moves n times faster around the timing dial, promising a sensitivity that improves in proportion to n, rather than the timid square root. Dazzling on paper, fragile in practice, because any uncorrected loss or dephasing nibbles that advantage away faster than it grew. The magic, however, is not only in exotic states, but in how you ask questions. Adaptive metrology listens to early outcomes and retunes the probe in real time, so that each new chunk of data lands where it is most informative. You can picture a sailor taking short tacks toward an unseen lighthouse, turning the wheel after every glint of feedback to stay on the steepest slope of the information curve, and in timing that means choosing interrogation intervals, probe phases, and detection thresholds that keep your estimates in the region where a small change in the unknown produces the biggest change in what you measure. Pair that with modern estimation methods, Bayesian filters that keep track of your belief as a probability landscape rather than a single guess, or algorithms that tolerate outliers without overreacting. And you convert raw detections into a time estimate that tightens like a well-tied knot, rather than ratcheting forward in uneven lurches. Crucially, quantum metrology is honest about costs, squeezing demands overhead to generate and stabilize non-classical light. Correlations in atoms require careful control of interactions and can introduce new channels for loss. Entanglement across a network of clocks raises alignment and calibration challenges that a single lab clock never faced. Yet even modest resources move the needle. Several decibels of optical squeezing or a few decibels of spin squeezing are enough to turn months of averaging into days, or watts of probe power into milliwatts. And those gains stack with better isolation and smarter estimators rather than replacing them. So progress compounds rather than cannibalizes itself. The frontier pushes two complementary directions at once: miniaturization and networking. Chip-scale devices seek to bring squeezed light sources, quiet cavities, and cold atoms onto integrated platforms where vibration and temperature are tamed by design rather than by acres of optical tables, while fiber-linked or free space-linked arrays of quantum-enhanced nodes cooperate like a phased array, comparing phases directly instead of trading coarse timestamps and subtracting delays. In such a network, common mode noise can be cancelled, and the remaining signal can be summed coherently, letting many modest instruments beat a single grand one. And because some of the correlations cannot be faked, the network gains integrity as well as precision, detecting tampering much the way quantum cryptography detects eavesdroppers. You might ask whether these tricks violate the spirit of no free lunch, and the answer is that they pay with ingredients classical strategies left on the table: the shape of fluctuations, the geometry of information in phase space, and the choreography of many body correlations. By spending those wisely, you do not conjure sensitivity from nothing. You redirect uncertainty away from your dial and into a drawer you have decided not to open, all while respecting the bookkeeping of physics. When losses loom large, you adjust the plan, use gentler squeezing that survives the path, distribute resources across time so that early measurements scout and later ones refine, or invoke error mitigation tactics that sense and subtract known drifts before they masquerade as timing jitter. The practical markers of success are beautifully down to earth: improved Allen deviation curves that bend downwards sooner, clocks that reach a given stability in a fraction of the averaging time, sensors that resolve smaller accelerations or field changes within a single measurement cycle, and communication links that align bits and symbols with less guard space, freeing bandwidth. The same principles spill into imaging and spectroscopy, where quantum-tailored light and matter make edges sharper and lines thinner without blasting the sample or the detector with brute force power. If there is a quiet philosophy behind all this, it is that precision is a story about structure, not merely collecting more data, but collecting the right data in the right collective state and reading it with the right question. Quantum metrology invites you to treat randomness as clay rather than granite, to sculpt it around what you care about so time reveals itself more quickly, and to accept that the price of such sculpture is care. Care in preparation, care in shielding, care in inference. And when you carry that back into ordinary life, the echo is gentle but clear. Better timing rarely comes from shouting louder or waiting forever. It comes from aligning efforts, reducing the noise that matters, and asking for exactly what you intend to use, so that the next second you measure is not just another tick, but a cleaner answer to a carefully posed question. Timelike entanglement, correlating across moments. You know how two people can share a secret look across a room and act in perfect sync. Timelike entanglement is that kind of secret, but stretched across moments instead of meters, a way for quantum systems to be woven together through time, so that what you see later and what you prepared earlier are tied by correlations. No classical story of the system just had a hidden plan can explain. And learning how this works changes how you think about memory, causality, and what it means for events to be connected. Start with the ordinary picture where a system moves from now to later by carrying a set of properties forward like a sealed envelope. The present determines the future, maybe with some noise, but always by passing along a readable state. And contrast it with the quantum picture where you can create a relationship that does not fit any envelope model at all. You let a system interact briefly with a reference, an ancilla, a quantum memory, even another mode of the same field, and then separate them in time. And when you bring information from the two moments together, you find patterns that cannot be produced by any chain of classical causes with hidden variables, because the state between the two times never existed as a single, fully owned set of facts. In practice, This looks like a simple choreography with surprising consequences. Prepare, touch lightly, wait, touch again, and only after you. Compare the joint data from both touches. Do you see that the earlier and later outcomes are braided more tightly than chance or classical memory allows? One clean way to feel it is with a single photon or a single spin visited twice. You first create a controlled superposition and let a tiny piece of information about it be parked in a quantum memory. Then you step aside and let time pass. No wires, no continuous contact. And later, you interrogate the system again with a setting chosen after the first step is already done. If nature were classical under the hood, the best it could do would be to leave you with correlations bounded by a familiar ceiling. But experiments show that, with the right preparation and the right kind of readout, you can beat that ceiling in the time domain, revealing that the pair, earlier-later, can be as non-classically linked as the pair here-there in spatial entanglement. Crucially, nothing supernatural or paradoxical happens. No messages go backward. No choices in the future rewrite the past. The correlations only emerge when you bring records together and analyze them, just as spatial entanglement never lets you signal faster than light, even though joint statistics break classical expectations. You can build time-like entanglement in many physical languages without drowning in jargon. In solid-state systems, an electron spin can share quantum information with a nearby nuclear spin that sits still for a long time. So a brief dance now sets the stage for a decisive step later. In superconducting circuits, a qubit can spill part of its quantum state into a loop of coaxial cable that acts like a delay line, then interfere with that returning echo at a later gate, producing correlations across well-defined intervals. In optical platforms, you can carve a light field into temporal modes, let them interact at different times, and then measure them jointly so that your detector reads out a pattern that only a time-entangled state could create. Across all of these, the shared ingredient is not distance, but the careful storage and retrieval of phase relationships, so that the before and after are treated as one quantum object sliced into two moments. Treating it as a tool rather than a curiosity immediately suggests uses. You can improve certain sensing tasks by arranging interactions so that a system's present response carries a subtle imprint of a past probe, amplifying weak effects that act over long intervals. You can make quantum communication schemes that are more robust to loss by spreading correlations across time slots and decoding them jointly, so that a missing piece does not doom the message. You can even design processors where a small set of hardware elements achieve complex behaviors by reusing themselves across time with entangled scheduling, turning a short-term quantum memory into a performance multiplier. In all these cases, the gain comes from refusing the classical rule that each step must be statistically independent once you condition on the current state. Time-like entanglement smuggles useful structure across the boundary between moments. The boundaries are just as instructive as the promises. To keep a link across time, you need a refuge for fragile phase, which is why the quality of your quantum memory, the thing that holds a piece of the state while the clock ticks, sets the horizon for what kinds of temporal correlations you can tap. Noise that merely blurs a classical variable is deadly when it reveals which alternative the system would have taken, because that knowledge leaks to the environment and collapses the joint story into an ordinary history. Engineers fight back with materials and protocols designed to hide the most dangerous kinds of information from the outside world, to refocus internal drifts at chosen instants, and to read out only the combinations that preserve the non-classical thread, so that when you finally compare early and late records, you are still looking at a single woven pattern rather than two unrelated scraps. The theory side offers a clarifying lens that you can appreciate without equations. Instead of describing states at times, it describes processes that map what you do then into what you can see now, and in that language, entanglement is a property not just of things but of histories. Some sequences of events are more than the sum of their steps. and their non-classicality shows up as an inability to explain the joint statistics with any model that assigns pre-existing outcomes to all possible choices. This is why researchers talk about entangled histories or quantum causal structures, phrases that sound abstract until you remember that your lab protocol is a causal structure, and that if you design it cleverly, it can reveal the footprints of a connection that was never carried by a classical messenger. From a foundations perspective, this matters because it tests whether the weirdness of quantum theory is confined to separated objects or whether it also shapes how one object meets itself again later. The answer seems clear. Time does not wash away quantum structure by default. It can carry it forward just as faithfully as space carries it sideways, provided you do not let the environment eavesdrop in the wrong basis, and provided you agree to do your bookkeeping honestly by comparing the right joint data at the end. And there is an everyday moral hiding under the physics. Timelike entanglement reminds you that connection is not only about being close, it is about how you arrange interactions and what you remember. Two moments in your life can be more deeply linked than two places on a map if you protect the thread that runs between them, if you avoid leaking the meaning of a choice to a noisy world too soon, and if you choose your final readout in a way that honors the pattern you set at the start. In the lab, that discipline yields correlations that beat classical timing strategies and open new modes of communication and sensing. And in your day, it points to a gentler truth, that the future you prepare and the past you lived can meet in a way that is richer than simple cause and effect, provided you hold on to the right kind of quiet and compare your notes with care when the moment arrives. Temporal bell tests, non-classical across time. If you want to know whether quantum strangeness survives the march from one moment to the next, you do something audacious. You run a bell test in time, not across space, and you ask a single system two carefully chosen questions at two different instants to see whether its answers can be explained by a simple story of it always had definite properties, and my measurements did not disturb them. And when the data refuse that story, you learn that the non-classical thread can bind events separated by seconds just as surely as it binds particles separated by miles. The ordinary Bell test compares outcomes from two distant labs, but the temporal version collapses the geography into a timeline. Call the early experimenter Alice at before and the later one Bob at after, and each must choose between two kinds of gentle interrogations, record a yes or no, and later compute a special combination of correlations that any classical model with pre-existing values and harmless measurements must obey, a bound that acts like a speed limit for ordinary causality. Quantum mechanics. When you prepare the system in a superposition and choose your questions wisely, pushes those correlations beyond that classical ceiling, even though nothing travels faster than light and no message leaps backward in time, because the violation appears only after you bring the records from both instants together and compare them, revealing that the system was not carrying a fully formed set of answers through the interval in the way a classical envelope would. To appreciate what is at stake, picture a simple two-state device, a spin in a solid, a superconducting qubit on a chip, a photon traveling down a line that you can interrogate in different bases, which you can think of as different ways of slicing its identity. A classical realist would insist that at each moment the device possesses definite values for all the slices you might ask about, whether you look or not, and that a sufficiently careful measurement could peak without changing those values. But the temporal bell protocol drives a wedge between that comfort and reality. When you record correlations between answers at the first and second time for different pairs of questions, you find combinations that exceed the classical limit. And because your choices at the second time were not yet made when the first answer was written, no hidden preloaded script can reproduce all the statistics without allowing the early measurement to have influenced what was even meaningful to ask later, which is exactly what the quantum rule says happens when you measure incompatible slices in sequence. Skeptics rightly worry that maybe you just poked the system clumsily and destroyed the bound by brute disturbance. So the experimental craft has evolved a toolbox to make that excuse run out of room. Weak measurements that only nibble at the state, while still revealing just enough to build the needed correlations. Ideal negative result methods where you infer an outcome from the absence of a click, and therefore claim, with justification, that the system could not have been jolted by the detector, and interleaved control runs that calibrate how much unavoidable back-action your hardware introduces, so the remaining violation cannot be blamed on sloppy handling. In practice, demonstrations have spanned everything from nuclear spins in molecules at room temperature to trapped ions and superconducting circuits, and even temporal versions of the famous inequality used in spatial tests have been implemented with photons that are measured, delayed, and measured again, all agreeing on the same conclusion. If you hold on to quantum coherence across the interval, the time-ordered answers refuse to fit a classical ledger. The implications are both technical and philosophical, and they are best felt through concrete payoffs. A temporal bell violation becomes a certificate that a quantum memory truly preserved useful phase information between the two instants, not just a classical snapshot, which matters if you want to build repeaters for quantum networks or delay lines for processors. In sensing, the same logic tells you that a probe's response at a later time carries a non-classical link to its preparation, allowing you to amplify weak signals that act gradually by designing sequences that harvest those across-time correlations. In security, protocols can exploit temporal non-classicality to generate randomness on demand or to authenticate the freshness of a signal, because a forger, who only has access to classical records, cannot reproduce correlations that require coherence to survive the gap between questions. The limits are just as instructive. As you thicken the system with more particles, or push the interval longer, the surrounding world learns too much about which way the state would have gone if left alone, washing out the delicate pattern and dragging your correlations back under the classical ceiling. A graceful failure that maps where decoherence eats temporal quantum structure first. Engineers fight back with better isolation, with dynamical decoupling sequences that refocus slow drifts without erasing the very incompatibility the test needs, and with clever choices of questions that are maximally sensitive to the preserved coherence while being minimally sensitive to the noise your platform cannot avoid. A subtle conceptual point worth carrying with you is that temporal bell tests are not about time travel or retrocausality. They respect the arrow of time by design, and the later choice never changes the earlier record. What they crush instead is the notion that there existed a joint assignment of definite answers for all the possible questions at all times, waiting to be revealed by a sufficiently gentle peak. Once you accept that, the violation is less a puzzle and more a diagnostic. It tells you that the state in between was not a classical fact, but a potential that crystallized differently depending on which question you asked when, and that the laws of physics forbid you from treating incompatible slices as simultaneously real across the whole interval. This view also dovetails with a newer, process-based way of thinking that you can appreciate without equations. Rather than listing states at each time, you characterize the transformation that carries interventions at the first instant into probabilities at the second, and temporal non-classicality shows up as a feature of that transformation that cannot be decomposed into a classical, forward-in-time channel aided by a hidden variable. When experiments observe the forbidden correlations, they are witnessing a genuinely quantum causal structure, one where the possibilities at the second time are not merely filtered by the first, but shaped by it in a way that resists reduction to pre-written outcomes. If you want a practical rule of thumb as you build or judge devices, use this. Whenever someone claims to have preserved quantum advantage through a delay, ask for a temporal bell-style witness. Whenever timing claims push toward the limits of what classical averaging could achieve, ask whether across-time correlations were engineered and protected rather than merely assumed. And whenever a sensor's response is said to integrate tiny effects over long intervals, ask how the sequence avoids letting the environment learn which path the evolving state would take, because that learning is exactly what turns violations off, and there is a softer echo for the rest of your life in this otherwise sharp experiment. The way you question a system over time matters as much as the answers you get, and genuine insight arrives when you compare notes from different moments without pretending those moments shared a single, pre-written truth. Temporal bell tests teach you to design your questions so that what survives the interval is the kind of coherence that carries meaning, to diagnose when noise has quietly written your story for you, and to recognize that some connections across time are deeper than any chain of hidden assumptions can capture, so that when you finally align your early preparation with your late readout and see the classical bound give way, you feel not confusion, but a calm recognition that the world is richer than envelopes, and that understanding it requires both patience and the courage to ask incompatible questions at just the right times. Weak measurements of past and future. What if you could ask a quantum system a question so gently that it barely notices, jot down the faintest hint of an answer, and only later decide whether that answer will count, after you've seen how the story ends? That is the strange but practical idea behind weak measurements of past and future, where you pre-select a state to begin with, let a feather-light probe brush against it, then post-select a final outcome, and keep only the runs that finish the way you choose, averaging many vanishingly small nudges to reconstruct information that ordinary, stronger measurements would have destroyed. In a standard measurement, you slam the door and force the system to declare a definite value, collapsing superpositions and scrubbing away delicate interference. But a weak measurement uses such a tiny coupling that each trial yields almost no information and causes almost no disturbance, like placing a stethoscope against a soap bubble rather than pressing a thumb. And by repeating this gentle touch over thousands or millions of copies, and then sifting the data based on a later filter, you can read meaningful trends about where the system was, or what it tended to do, in the interval between preparation and final check, without shattering the very behavior you hope to study. The basic choreography is simple to describe even if it took decades to master in the lab. You prepare many identical systems in an initial state, pre-selection. You couple them very weakly to a meter, perhaps a light beam's angle, a tiny current in a superconducting loop, or a phase in a microwave resonator, so weakly that the meter's pointer shifts hardly at all for a single run, and then you perform a decisive measurement at the end, post-selection, keeping only those runs where the final outcome matches a choice you made. When you average the tiny pointer shifts over just that filtered subset, you uncover a quantity called a weak value, a number that can lie far outside the ordinary range of eigenvalues you would expect from strong measurements, not because the system broke a rule, but because conditioning on a specific future result changes which parts of the earlier superposition mattered for the data you kept, much like averaging the height of a crowd. Only after you've selected people who could pass through a tilted doorway biases the mean in unexpected ways. Nothing supernatural has happened. You cannot use post-selection to send a message to the past or guarantee a desired outcome, but you have legitimately extracted a kind of time-sliced expectation that is defined by both boundaries of the experiment, a two-time portrait that speaks to how the system's amplitude flowed from its beginning toward the particular end you chose to examine. This gentle then filter approach does more than tweak philosophy. It unlocks concrete capabilities that strong measurements can't offer without wrecking the scene. In optical interferometers, you can weakly tag which path light leans toward, while leaving the interference almost intact. Then, by sorting the data based on a later detection port, draw streamlines that resemble average trajectories through the device. In solid-state qubits, you can probe a component of spin so softly that coherence lives on, and after post-selection, you infer subtle drifts that a projective readout would have drowned. In atomic and photonic experiments, you can even perform direct measurements of a wave function's profile by weakly sampling one variable and strongly reading a complementary one, mapping out how probability amplitude is distributed without the iterative, fragile reconstructions of traditional tomography. And in precision sensing, you can exploit the fact that weak values can be very large, an anomalously long lever arm that amplifies tiny beam, deflections or minute phase shifts into pointer moves that stand out above certain technical noises, an effect that has helped detect angles and delays too small for standard meters, though with the important caveat that amplification never beats fundamental quantum limits unless your noise is dominated by the very technical imperfections the scheme suppresses. The deeper lesson is about time's role in inference. When you condition on a specific future outcome, your best estimate of what a gentle probe saw earlier can change, not because the future rewrites the past, but because the statistics that matter to your question are those of the subset that actually led to that outcome. In this sense, weak measurements are a laboratory for time-symmetric thinking, where you treat the experiment as bounded by two anchors, the state you launched and the result you accepted. And you ask what small, nearly non-destructive touches in between can truthfully say about the corridor connecting those anchors. Framed this way, controversies around weak values become clearer. They are not promises of impossible readings, but conditional averages with well-defined recipes that match quantum theory's rules, when you compute them correctly and compare only the data you promise to keep. Still, the craft is demanding, and the boundaries teach you as much as the successes. If your coupling is not truly weak, you start to kick the system around, and your conditional average slides back toward ordinary measurement results. If your post-selection is too rare, you may inflate statistical errors or invite selection biases that mimic anomalous values without revealing anything deep. If your environment leaks witch path information, the fragile correlations that make weak values meaningful evaporate, and your meter registers noise, not nuance. Careful experiments therefore document the coupling strength. Track losses calibrate the meter's baseline drift and compare multiple post-selections to show that the reported weak values move exactly as the theory predicts when you shift the boundary conditions. Seen as a toolkit rather than a loophole, weak measurements offer a map for getting answers to questions we once thought unaskable. Where did the particle spend more of its time while the interference pattern formed? How does a qubit's phase meander between two chosen endpoints? Which tiny influence nudged our sensor during the interval we care about? All answered not by a single dramatic shot, but by harvesting tiny, almost intangible hints that add up when treated with respect. The payoff is both practical and philosophical. Practical because it enables new kinds of diagnostics and metrology that keep coherence alive while still learning something useful. Philosophical because it nudges you to think of cause and effect as a conversation between preparation and readout, with the meaning of faint clues clarified only after the ending is known. And perhaps the softest, most human echo of this physics is the reminder that not every truth is accessible to a shove. Sometimes the only honest way to learn about a fragile process is to touch it lightly and be patient, to let many near-silent observations accumulate, and to interpret them in the context of how the story actually unfolded, so that when you look back and say, "This is what was happening in between," you are not claiming to have frozen the world, only to have listened well enough and with the right future in view, to reconstruct a faithful trace of the path without erasing the path itself. Time bin encoding in photonics. Teach light to speak in syllables and you can send secrets through a storm. That is the promise of time bin encoding in photonics, where a single photon is carved into two or more well-timed knocks on the detector door. An early tap, a late tap, or a controlled blend of both, and the relative phase between those taps carries information as surely as ink on a page, yet with a toughness that ordinary polarization tricks can't match over long, noisy fibers. The preparation is conceptually simple, even if the hardware is precise. You start with a short pulse of light and split it along two paths of different lengths. So part of the pulse arrives early and part arrives late. Then you recombine the paths so that the photon's identity is not either early or late, but a coherent superposition that remembers both. And by tuning a phase shifter on one arm, you set how the early and late syllables interfere when a matching analyzer recombines them at the receiver. Now the bit lives in time, not in direction or polarization, which means a buried fiber that scrambles polarizations with temperature and vibration still preserves the crisp spacing between the knocks. And as long as your clocks agree on where early and late fall, the message survives with remarkable grace. Push a little deeper and the elegance multiplies. The same unbalanced interferometer that creates a single time bin qubit can be chained into arrays that produce higher dimensional alphabets, with 3, 4 or more bins acting like letters beyond simple yes and no, allowing you to pack more information per photon and to tailor protocols that tolerate more noise. Pair a pulsed pump with a nonlinear crystal and you can generate entangled photon pairs whose when is linked rather than their where, so that a coincidence in a distant station tells you the early-late superpositions matched, even though neither photon possessed a definite arrival time by itself. And you verify the non-classical bond with a 2-interferometer test, where only the early and late histories can meet and interfere, drawing fringes that swing as you dial the phases in tandem. Evidence that time, handled gently, is as good a stage for quantum correlations as space. The engineering has a rhythm you can learn. The bins must be wider than the timing jitter of your detectors, yet narrow enough to outpace slow wander in the channel. Dispersion in glass wants to smear the taps into blurs, so you pre-compensate with tailored fiber, or balance with opposite dispersion, so that the early and late syllables keep their shape when they arrive. A pilot tone or auxiliary laser keeps the interferometer's phases aligned by feeding a control loop that nudges heaters or modulators to cancel drift minute by minute, and superconducting nanowire detectors, with their clean timing stamps and low noise, let you pull the bins closer together to raise data rates without confusing knocks that ought to be distinct. Because the alphabet is temporal, you can route and process it with compact loops on a chip. Integrated beam splitters and Mach-Zehnder interferometers recreate the long and short paths in millimeters of waveguide, thermo-optic or electro-optic elements set, and stabilize phases without a forest of bulk optics. And switchable delay lines write and erase bins on demand, turning a tabletop experiment into a palm-sized engine you can network. That same integration makes time-multiplexed quantum computing schemes practical, where a single loop with variable delays lets one physical device act like many logical modes, and cluster states, those webs of entanglement used for measurement-based processing, can be woven in the time domain as a train of correlated bins, rather than as a sprawling array of separate fibers. The security angle is not marketing fluff, but physics at work. In quantum key distribution, time bin encoding resists the slow polarization drifts that plague buried networks and goes long distances with fewer recalibrations. Decoy state methods, where you vary the brightness of pulses to smoke out photon number splitting attacks, translate cleanly into the time bin setting. And because the receiver's interferometer only produces the right fringes for the intended phase relationships, certain spoofing strategies that rely on classical timing cannot mimic the full statistics without exposing themselves in error rates. Still, honesty demands the footnotes. Multi-photon emissions from your source can leak information unless you shape and monitor them. Side channels can creep in if the early and late bins have distinguishable spectra or shapes. And free space links must tame atmospheric jitter that shakes arrival times. Problems real teams solve with spectral filtering, careful pulse shaping, adaptive gating, and watchdog detectors that flag anomalies rather than letting them ride. Time bin entanglement also speaks the dialect of memories, which matters for building repeaters. Rare earth-doped crystals and other atomic media that store light as a collective spin wave can accept and release early-late superpositions with their phase intact. Provided you tailor the absorption pattern, the memory becomes a cabinet with labeled shelves for the bins, so you can catch a photon, wait out a lossy span of fiber, and re-emit it later without losing the rhythm that made the state useful. Tie several such memories together, and you stitch a longer link from shorter pieces, swapping entanglement across stations without ever having to balance polarization through every kilometer of cable. If you prefer the big picture compass rather than the wiring diagram, carry this. Time bin encoding turns the inevitable tick of your clock into an ally by phrasing quantum information as a poem whose meter you control. The practical benefits: robustness in fiber, compatibility with chips, clean scaling to higher alphabets, are why it keeps winning field trials and why deployed networks increasingly lean on it to move beyond lab bench heroics. The limits you must respect: detector jitter, dispersion, path length drift, security bookkeeping, are not walls but design inputs, and the most successful systems treat them as parameters to be shaped rather than nuisances to be ignored. And there is a soft lesson beneath the optics. When you encode meaning in when rather than where, you learn to respect the pauses as much as the pulses, to build reliability by staging events in a pattern the world can't easily scramble, and to recover coherence, not by shouting louder, but by timing your syllables so they meet exactly where they should. Teach light to knock early and late with intention, and the network hears a sentence that can travel oceans of glass without losing its sense. A quiet demonstration that sometimes the easiest path to clarity is to let time itself become your alphabet. Indefinite, causal order, and timers. You were taught that cause comes before effect, the way footprints come before the path behind you. But quantum physics quietly offers a stranger choreography in which before and after can be placed in a controlled superposition, so that two tasks A and B are performed in an order that is neither strictly A then B nor B then A until you choose how to look. And the surprise is that this indefinite causal order is not just a philosophical puzzle. It can be turned into a timer, a metrological tool that estimates delays, phases, and rates more precisely than any setup forced to pick a single timeline. To feel the shift, imagine two black boxes that each imprint a tiny, unknown time shift on a signal, perhaps a faint phase, advance in an optical pulse or a minor latency in a microwave gate, then Ask the ordinary question, what happens if I pass my signal through A and then B? And you get an answer, but one that is limited by how those shifts and their noise stack. Now imagine a control qubit, an internal switch that can coherently decide the order, such that if the qubit points up, the signal sees A then B, and if it points down, it sees B then A, and you prepare the qubit in a superposition so both sequences happen at once. When you finally recombine the two histories and read the control, interference between the two orders makes the detector sensitive not just to the individual shifts, but to how the actions fail to commute, and that extra sensitivity can amplify, isolate, or cancel features of the total delay that a single fixed order would smear together. In practical language, the superposition of orders turns the network itself into an interferometer whose fringes are written in the logic of who came first, and by watching those fringes slide as you tweak a knob, you can estimate a microscopic timing parameter with fewer particles, less power, or less averaging time than a classical arrangement would require. This is not hand-waving about time travel. Nothing in the protocol lets signals run backward or messages escape into the past. And the payoff appears only when you bring the joint record of control and target together, just as with any other interference experiment, where no single arm tells the whole truth. The difference is architectural. Ordinary circuits are drawn on a flat page where arrows have a fixed left-to-right order, while indefinite order is more like a folded page where arrows can cross beneath one another in a coherent way, and the fold is controlled by a quantum system you can prepare, steer, and measure. Researchers describe this with process matrices, maps that specify not only what each box does, but how the possibility of one box feeding another is itself a quantum variable. And in that language, causal indefiniteness becomes a resource in the same sense that entanglement and coherence are resources, something you can consume to gain an operational advantage, certify with witnesses, and lose when noise leaks which path the control took. As a timer, the quantum switch has a particular talent. It can refocus certain classes of noise that plague delay measurements by arranging for that noise to appear identically in both orders and thus cancel in their interference, while leaving the parameter of interest, say, the small extra latency in A relative to B, to survive as a clean, measurable shift of the control's readout. You can picture a pair of phase shifters whose drifts wander with temperature and vibration, terrible for long-term stability, but placed in a superposed order, they imprint the same random wander on both branches. So the wander becomes a common mode wash that drops out when the two orders interfere, and the remaining structured difference writes bright, narrow features you can track. You can push this further by designing A and B so that the thing you want to estimate only shows up in their non-commuting part, which the switch isolates like a spotlight, while a fixed order would let other effects masquerade as the quantity you care about. There are simple, hardware-friendly incarnations of these ideas. In photonics, the two boxes can be paths through a pair of devices whose phases or delays you wish to compare, and the control can be encoded in a separate degree of freedom, so that a single photon carries both the question and the switch. In superconducting circuits or trapped ions, the boxes can be gates applied in alternative sequences controlled by a qubit, with the readout built into the same cryogenic electronics that already run the processor. In each case, the figure of merit is the slope of the final signal with respect to the unknown parameter. The steeper the slope, the less noise you need to resolve a given change, and superposed order steepens that slope by turning algebra, A then B versus B then A, into a phase difference you can see. The limits, as always, live where the world insists on knowing too much. If the environment learns which order occurred, through stray leakage, distinguishable timing jitter, or spectral signatures that tag A before B differently from B before A, the interference between orders fades and the metrological advantage erodes. Engineers answer with identical spectral shaping of the two branches, matched losses, dispersion compensation so early and late spectral content look the same, and active stabilization that keeps the control and target synchronized without leaking the very which order information that must remain hidden. In parallel, theorists build causal witnesses, measurement patterns that certify you truly used an indefinite order rather than an undocumented classical mixture of orders, because only the former explains the observed enhancement honestly. What makes this more than a niche trick is how it complements other quantum resources instead of competing with them. You can feed squeeze light into an indefinite order circuit to reduce the readout's technical noise, while still enjoying the commutator sensitivity, or entangle many controls to run several order superpositions in parallel and sum their information like an antenna array sums faint radio waves, or distribute order superposed tasks across nodes in a network, so that a timing reference shared between cities benefits, both from two-way stabilization and from order interference that cancels path asymmetries, that round-trip methods alone cannot tame. All of that fits naturally with chip-scale integration, where long delays, phase shifters, and beam splitters live as compact waveguides and heaters, and where adding a control qubit is a matter of a few more elements rather than a new building. You may wonder where this touches the frontier of physics beyond instruments, and the honest answer is twofold. First, as a matter of principle, it shows that the order of events can be a quantum variable in the lab, not only a speculative feature of exotic spacetimes, and learning to manipulate it teaches you how to talk about causation without assuming a fixed background clock. Second, as a matter of practice, it offers a way to probe tiny gravitational time offsets and relativistic effects in tabletop settings, because the interferometer in order space can be made sensitive to delays induced by motion or height differences while using the superposed order to cancel bigger, dirtier drifts, a strategy that could sharpen chronometric leveling, interlab comparisons, or fieldable sensors that need to detect sub-picosecond shifts in chaotic environments. The softest lesson, though, is about design. A timer does not have to be a dial that runs against a backdrop of fixed before and after. It can be a question you ask twice in different ways and only decide the order at the end, letting the world's response interfere with itself so the part you care about stands out. When you start to think this way, you stop assuming that the architecture of a measurement, the sequence of steps, is a constraint and start treating it as a knob. And that shift is as much philosophical as technical, because it teaches you that sometimes the most honest way to learn how long is to let who comes first blur until the difference becomes visible. Then read that difference with respect and care. In the hands of a good experimenter, indefinite causal order is not a paradox to admire, but a clock to build, a way to place the schedule of operations into superposition so that time itself becomes easier to hear, and the world, for a brief moment, tells you more than it would have if you had insisted on marching in a straight line. Entropy, information, and temporal asymmetry. You feel the arrow of time most clearly when a hot mug cools on your desk and never reheats itself, and that quiet one-way slide is the heart of temporal asymmetry. The microscopic laws that shuffle atoms forward and backward in principle make no distinction between past and future, yet at the scale you live in, messy, many-body systems overwhelmingly move from ordered, special arrangements toward typical, scrambled ones. And we give that drift a name. Entropy increases. The key to understanding this without myths is to treat entropy as a count of possibilities consistent with what you can actually see and control, coarse-grained descriptions. So a tidy deck of cards has low entropy because few microarrangements look like perfectly ordered, while a shuffled deck has high entropy because an enormous number of microarrangements look equally random to your eyes. And when you let dynamics run, the system roams through microstates in ways that, almost always, spread out into those more numerous, more typical regions. That, almost always, is not a loophole, but a statistical certainty. In tiny systems, short times, or with deliberate feedback, you can catch fluctuations that go the wrong way. A few molecules happen to cluster. A Brownian particle gives back energy. But the modern fluctuation theorems show that negative blips are exponentially unlikely compared to positive ones. And when you average the ledger, honestly, you recover the second law's plain summary that entropy increase is the rule, not the exception. If entropy is about possibilities, information is about distinctions. And the marriage between them is practical, not poetic. Every bit of reliable information you gain about a system reduces the number of microstates compatible with your description. Every bit you erase in your computer, or in your head, if you were a physically perfect demon, must be paid for by dumping at least a small amount of heat into the environment. The cost of clearing a memory register is real and proportional to temperature, which is why Maxwell's impish gatekeeper, who tries to sort fast molecules to make one side of a box hotter and the other colder, cannot win forever without heating something else off stage. The demon's trick is undone by bookkeeping. Yes, measuring can be done gently, but the storage and reset that make the information useful have a thermodynamic price. And the net effect is that any apparent reversal of entropy in one place is accompanied by a larger increase somewhere else, restoring the arrow when you include the whole apparatus in the story. Seen this way, a record is not a magical imprint, but a physical correlation that costs something to create and easy to lose. A footprint in mud, a photograph on a sensor, neuronal changes after learning. All are patterns in matter that align with a past event and are robust enough to persist as the surroundings jostle them. And those correlations themselves eat available order. They lock part of the world into a more specific state at the price of dispersing energy and increasing entropy elsewhere. That is why memories point only one way in time, even though the equations do not. There are countless microscopic histories that lead from a low entropy past to a present with records of that past, but essentially none that lead from a future, low entropy state to a present full of anti-records that would let you read the future, because the universe did not start with those fantastically special arrangements. This brings you to the most important ingredient hidden in plain sight. The arrow you experience depends on boundary conditions, not a secret asymmetry in the day-to-day rules. The early universe was extraordinarily smooth in its mass distribution, low entropy, given how many more ways there are to make a lumpy, clumpy cosmos. And as it expanded and cooled, it opened up an enormous phase space of ways matter and radiation could arrange themselves. So entropy had room to grow. Gravity flips your flatland intuition here. For a gas in a box, spreading out is high entropy, but for self-gravitating matter, clumping into stars and galaxies, and ultimately, black holes increases entropy because there are vastly more micro-arrangements corresponding to many small bodies and deep gravitational wells than to one perfectly smooth fog. That is why black holes, with their enormous capacity to hide microscopic details behind an event horizon, carry the largest entropies we know how to talk about, and why the long-term trend towards structure formation and eventual thermalization is, paradoxically, an entropy rise driven by gravity's hunger for inhomogeneity. You might ask whether the subtle asymmetries of particle physics, those tiny violations of certain symmetries in rare decays, set the arrow for you, and the answer is humbling. While those effects matter for why matter survived over antimatter in the early cosmos, they are not responsible for your tea cooling or your eggs scrambling. The mundane arrow that shapes your day is a statistical emergence from abundant degrees of freedom starting in a special, low-entropy configuration, with the bias locked in by the fact that there are so many more ways to be typical than to be special. Two classical puzzles sharpen this picture and, properly framed, dissolve. Loschmidt's paradox asks why dynamics that are reversible at the micro level lead to irreversibility at the macro level. And the reply is that nothing in the laws prevents a glass from unshattering if you precisely reverse every microscopic motion. But the set of states that would make that reversal happen is unimaginably tiny compared to those that lead to ordinary spreading. So you never prepare them by accident. And if you did, the slightest nudge from the rest of the world would spoil the show. Poincaré recurrence tells you that a closed system must, given absurdly long times, come arbitrarily close to its starting point. And that is true in principle, but irrelevant in practice because the recurrence times grow so explosively with system size that the universe will have erased the stage long before the actors retrace a step. Both puzzles remind you that possible is not the same as plausible. Quantum mechanics adds a modern twist without betraying the core story. The Schrödinger equation runs time symmetrically, yet when many parts of a system become entangled with many parts of the environment, the information you would need to reverse the film is spread into correlations you cannot access, a process we call decoherence that selects robust, classical-looking patterns and makes interference between macroscopically distinct alternatives effectively vanish. Decoherence is not the arrow by itself, but it explains why records look stable and why probabilities of everyday events settle down, while the low-entropy past tells you which direction those stable records will point. Put differently, entanglement growth and coarse-grained ignorance cooperate. The first hides the microscopic details that would enable reversal. The second declares them irrelevant to your macroscopic questions. And together they make forward feel inevitable. The union of entropy and information also sets budgets for technology. Erasing errors in a computer has a thermodynamic flaw you cannot beat by clever coding. Compressing data approaches limits set by the distributions of signals you actually send. Refrigeration and heat engines trade useful work for expelled entropy in ratios bounded by temperature. Even the fidelity of your clocks and sensors must contend with the fact that extracting more distinguishing power usually means arranging states that are less typical and therefore require more careful isolation and more work to prepare. There are shortcuts and clever detours, feedback that harvests fluctuations, engines that exploit known correlations, protocols that move entropy into places you do not mind warming. But none of them repeal the bookkeeping, they only write it with finer pen. If you want to hold one image at the end, make it this. Temporal asymmetry is a property of the universe's story, set by rare initial conditions and read out by systems that forget the details they do not track. Entropy measures how many ways the hidden parts can arrange themselves while leaving your visible summary unchanged. And information is your power to reduce that ambiguity by establishing and keeping correlations. Every time you tidy a room, write a file, or take a photograph, you push a small island of matter into an unlikely state, and you pay for it in heat and entropy elsewhere. And every time you let go, that island drifts back toward the sea of typicality. The arrow is not a law etched in stone, but a tide driven by numbers so overwhelming that they feel like fate. And learning to see it clearly does not make the world less mysterious. It makes the mystery honest. The past looks special because it was. The future looks open because there are so many more ways for it to be. And your knowledge sits in the narrow channel where careful records resist the blur just long enough for you to call them meaning. Arrow of time from entanglement growth. Stand close to a quantum many-body system at the instant it's set in motion, and you can watch a different kind of sunrise. Entanglement spreading outward like first light across a valley, joining regions that were strangers a moment ago into a single, stitched landscape. This quiet expansion, not heat or friction, is what can give time a direction, even when the fundamental equations themselves are indifferent to past and future, because as correlations proliferate, they reorganize what any small part of the system can truthfully be. And that reorganization almost always proceeds one way under ordinary conditions, toward greater interdependence, so that a patch you inspect later looks more mixed, more typical than it did at the start, even though the whole remains in a perfectly crisp quantum state. The operational picture is simple to hold. Prepare a lattice of spins, atoms, or qubits in a clean, low-entangled configuration, nudge it with a quench or a controlled interaction, and then step back as pairs of disturbances race outward in opposite directions, laying down threads of correlation as they go, so that two sites separated by a distance d do not influence each other, immediately but only after a time proportional to d, an emergent light cone that sets a speed limit for information flow, while any small region you grab along the way looks increasingly tangled with its surroundings, as if someone were quietly mixing ink into water just outside your field of view. That growing tangle gives the region a rising entropy when you ignore the rest, not because anything has been lost, but because the knowledge needed to specify the part now lives in the whole, and the whole is hard to hold in your hands. If this sounds like a semantic trick, experiments have made it physical. Cold atoms in optical lattices show light cone-shaped spreads of correlation after sudden changes. Chains of trapped ions and arrays of superconducting qubits let researchers watch entanglement growth by sampling clever randomized measurements. Rydberg atom platforms draw real-time maps of how an initially simple pattern evolves into a web of long-range ties. Across devices and materials, the theme repeats. Start simple, let dynamics run, and typical evolutions bury local order in shared structure that takes longer and longer to reverse as the web thickens. So the natural clock you read is the width of that web, not the tick of a dial. What makes this a genuine arrow rather than a convenient metaphor is that the same unitary rules that allow perfect reversibility do not make reversal likely. In principle, you could thread the needle by applying a precise time reversal operation that unwinds every phase and reconnects every thread, yet the control needed scales cruelly with the size and complexity of the state, and the slightest mismatch lets the outward growth resume. So for all practical purposes, the direction of increasing entanglement is as robust as any thermodynamic arrow you've met. In chaotic systems, those whose interactions rapidly shuffle information across many degrees of freedom, The growth is brisk and soon saturates at a value set by how big your patch is, leaving local observables looking thermal even though no heat bath was present. In integrable systems where conserved patterns constrain motion, the growth is more orderly and often slower, like ripples instead of surf. In strongly disordered settings that impede transport, the spread can be incredibly sluggish, creeping forward logarithmically in time. So the arrow exists, but advances with the patience of moss, different tempos, same direction. A helpful way to feel the mechanism without equations is to focus on bookkeeping. At the start, you can describe a small region with a short list of facts, because it shares little with its neighbors. As interactions weave histories together, the shortest faithful description of that same region lengthens unless you also keep track of the rest. And if you refuse to carry the global ledger, as you must in practice, the region's best description becomes a statistical one, a mixed state with more entropy than before. The rise is not mystical. It's a payment for ignoring the correlations you helped create. And the payment tends to increase because typical evolutions create more such correlations than they destroy. That is why two snapshots taken in the same lab an hour apart can display very different complexity in their local pieces, even though the total complexity has not changed at all. The structure moved from inside the part to between the parts, and your coarse view experiences that as a one-way drift. There are useful edges and exceptions that sharpen the rule rather than undermining it. Frequent strong measurements can interrupt the weaving and, beyond a threshold, even arrest entanglement growth by repeatedly projecting the system into simpler patterns. The measurement-induced analog of freezing a fall, mid-air, which teaches you that the arrow depends not only on the interactions, but on how often you insist on crisp answers. Engineered disorder or constraints can bottleneck the spread so severely that records of the past survive for long times. A feature that is both a challenge for thermalization and an opportunity for preserving fragile quantum memories. And carefully choreographed protocols can create pre-thermal plateaus, where growth pauses as if time had oozed into tar before eventually resuming. A reminder that the arrow can bend without breaking when conservation laws temporarily fence dynamics in. From a design perspective, seeing time's arrow as entanglement growth gives you a practical dial to turn. By tailoring the geometry of couplings, you can set the effective speed limit for correlation spread, giving sensors time to read a disturbance before it dissipates into the crowd. By sculpting interactions to scramble information quickly, you can build devices that hide local imperfections under a blanket of global structure, which is the unglamorous core of certain error-tolerant schemes. By measuring growth rates, you can diagnose whether your hardware lives closer to the tidy world of constrained motion or the exuberant world of chaos, and you can choose the operating point that best suits what you're trying to do. Some tasks want quick mixing to wash away bias, others want slow growth to protect delicate order. Philosophically, the picture offers a gentle unification. The statistical arrow you feel in cooling coffee and the quantum arrow you infer from rising entanglement are two faces of the same story about how special beginnings become typical middles. One counts microstates compatible with a coarse description. The other counts how many relationships you've created that your coarse description refuses to carry. Both grow because most trajectories wander into the wide country of typicality, and only an astronomically careful steering keeps them on the narrow path back. And both can be read, moment by moment, by asking how much of the present resides within reach of a small patch, and how much has diffused into patterns that only the whole remembers. Perhaps the most disarming lesson is this. You do not need a hot bath or a random kick to feel time move forward. Only interactions that let parts talk to parts, and a willingness to look at less than everything. Under those two conditions, the world writes its history into connective tissue that thickens with every passing second. And while the grand equations would let you unwrite it in principle, the work required grows so brutally with the area you need to control that. In practice, the future is a room with more doors open than the past. If you want a compass sentence to carry away, let it be this. Time's arrow, at the quantum level, is the steady migration of detail from the places you can hold in your hands to the spaces between them. And as that migration proceeds, what was once easy to name becomes part of a larger sentence. You can only read by hearing the whole, learning to see that migration, measuring it, shaping it, sometimes halting it, turns an abstract slogan about irreversibility into a working handle, and it leaves you with a soft human echo, Relationships, once formed, are hard to unwind, and the more the world interlaces, the more your small corner looks like it has moved forward, because the rest of the fabric has learned too much of your story to let you go back to the way you were. Thermal time hypothesis. Heat begets time. You are used to treating time as the background canvas on which everything else is painted, a neutral grid that never asks who you are or how warm the room feels. Yet the thermal time hypothesis invites a different habit of mind. Imagine that the flow you call time can be extracted from the state of the world itself, that the rhythm of change is not supplied from outside, but is read off from how matter is distributed, how likely processes are to run forward versus backward, how a system at some effective temperature organizes its own balance of fluctuations. Heat, in this view, begets time by providing a built-in clock that ticks in step with the system's statistical order. The motivation is practical before it is philosophical, because in settings where no preferred external clock is available, think of a closed laboratory sealed from outside cues. Or, at grander scales, a generally covariant universe where geometry does not hand you a single master time. What counts as evolution must be defined internally, and the hypothesis says the right internal yardstick is the one singled out by equilibrium structure. The direction in which correlations relax, the parameter that makes detailed balance relations come out clean, the flow under which an observer's records look stationary on average, while deviations carry meaning. You can make this less abstract by thinking operationally. A thermometer placed in contact with a stable environment does not watch seconds. It watches ratios, how often a transition happens one way versus the other. And those ratios carry a natural scale that, when you stitch many such local stories together, defines a global parameter along which the system looks most steady overall. Choose that parameter, and the equations that describe your records simplify. Averages stop drifting, and the remaining changes are the ones that actually carry information. In that sense, thermal time is the bookkeeper that the state itself prefers, the unique way of labeling snapshots that makes equilibrium look like equilibrium rather than a film playing at the wrong speed. Notice the subtlety. This does not claim that temperature literally manufactures time, or that hotter objects age faster in a naive way. It says the statistical state you occupy selects a natural slicing of change and clocks that coupled to that state. Chemical oscillators, Brownian pointers, two-level systems interrogated by gentle probes, will read out that slicing most cleanly when they are tuned to the same equilibrium. If you move to a different state, the preferred slicing can shift. So the question, how fast is not answered in the abstract, but in relation to the milieu in which your clocks live. This relational flavor becomes especially useful when space-time does not supply a single universal tick. Inside a gravitational field, different regions disagree on rates for deep geometric reasons, and a thermal perspective helps tie local stories together by asking each region to define time with respect to its own equilibrium, and then to compare those definitions through the physical links, light, matter, signals, that actually carry records from place to place. In accelerating frames, the vacuum itself behaves as if it has a temperature. So an observer who rides that motion naturally organizes events using a parameter aligned with the apparent bath, and the consistency of their record keeping across distances depends on how well those thermal yardsticks can be reconciled at the boundaries where data are exchanged. The hypothesis also clarifies why certain procedures feel privileged in practice. When you analyze long-time series from a stable apparatus, you often rephase your data so that averages are constant and noise is symmetric around zero. You are, in effect, choosing the parameter that makes equilibrium look still and departures stand out, exactly the choice thermal time prescribes. And when you do precision spectroscopy or timing, you design your instruments to live near steady operating points where small signals tilt balanced flows rather than ride on top of drifting baselines. Seen through this lens, good metrology is not just about low noise. It is about adopting the internal time that the state prefers so that information arrives as cleanly as possible. Of course, the story has edges, and those edges teach you how far the idea reaches, far from equilibrium, where a system carries multiple, incompatible temperatures or supports currents that never settle. There may be no single thermal time, but rather a patchwork of local parameters, each honest within its domain. In strongly driven devices, the preferred labeling can itself become time-dependent, forcing you to update the yardstick as conditions change. And in microscopic experiments that preserve delicate superpositions, the notion of equilibrium that anchors the definition must be handled with care, because the very coherence you seek to exploit resists being squeezed into a simple statistical mold. Still, even there, the hypothesis does not crumble. It becomes a guide for what to measure. Look for the directions in which correlation functions stabilize, for the balances that hold on average, for the symmetries of your data that reveal the hidden frame rate at which your system tells its own story. Then call that frame rate time and keep the rest as signal. A common misunderstanding is that this perspective erases the arrow of time by making time a matter of choice. But the opposite is closer to the truth. Once you accept that the world started in a remarkably special configuration, the thermal time selected by that state points the same way as the everyday arrow, because it is precisely the parameter along which relaxation unfolds and records of earlier conditions accumulate in robust, redundant forms. The arrow is not imposed from the outside. It is discovered as the direction in which typical changes bring you toward the equilibria implicit in the state you inhabit. And the fact that many independent subsystems agree on that direction is what gives civilization the confidence to schedule, coordinate, and predict. There are also gentle payoffs for how you think about building and comparing clocks. If the flow you adopt comes from your environment's equilibrium, then a better clock is not one that defies its surroundings, but one that couples to them in a way that reads the preferred parameter with minimal distortion. In a quiet lab, that might mean stabilizing fields and temperatures so the state stays near the reference you assume. Outdoors, it might mean letting your oscillator listen to the very bath that will govern the signals you intend to receive, aligning your notion of a second with the statistics of the channel rather than fighting them with brute force. Either way, you learn to treat timekeeping as matching a language rather than imposing one. And if you step back to the broadest picture, the hypothesis offers a simple sentence that is both humbling and liberating. The world does not consult a hidden metronome, it carries its own. And when you listen to the cadence of fluctuations, to the balances that hold and the ones that give way, you are already hearing the clock that matters. You begin gently by noticing that a good description is the one in which equilibrium looks still. You wade deeper by tying your inferences to the state's preferred bookkeeping, and you end softly with the recognition that your minutes are not abstract strokes but negotiated measures between you and your environment. Heat as a whispering timekeeper, information as the ink that fixes moments on the page, and change as the steady breath that makes a sequence out of what would otherwise be a blur. KMS states, thermal time in algebraic QFT. Suppose you had to recognize equilibrium without ever touching a thermometer, with no privileged clock on the wall, only the behavior of the quantum observables you can probe. What would you look for? In algebraic quantum field theory, the answer is strikingly precise and oddly elegant. You declare that a state is at thermal balance if, when you let your observables drift under whatever notion of time evolution your system admits, the correlations you measure obey a special swap and shift regularity that encodes temperature in their pattern, a criterion known as the KMS condition. And from this single operational rule, a full portrait of thermal time emerges. To get your footing, replace the usual picture of particles and forces with a more austere stage. An algebra listing everything you could in principle measure, and a state that assigns expectations to those measurements. Dynamics are not a ticking stopwatch, but a family of consistent relabelings, automorphisms that tell you how each observable would look later, and equilibrium, rather than meaning nothing changes, means something subtler. The time-ordered way two observables talk to one another is related to the opposite order evaluated at a shifted moment by an amount set by the inverse temperature. So if you listen to the noise with enough patience, you hear a built-in cadence that does not care about your favorite Hamiltonian form, or even about having a global notion of time, only about the internal bookkeeping of the system itself. Viewed this way, temperature is not an external dial, but a label that falls out of the pattern of correlations, and thermal time is the parameter along which that pattern looks most self-consistent. This abstract sentence becomes concrete quickly. When your system really does have a good Hamiltonian and an honest clock, the KMS rule collapses to the familiar, imaginary time periodicity that underlies finite temperature. Field theory, the reason Euclidean methods work and why spectra at non-zero temperature can be organized into discrete ladders. But the algebraic formulation earns its keep in harder places where global time either does not exist or is not unique, such as curved spacetimes or wedges carved out by accelerating observers. There, a single state can look warm relative to one flow and cold relative to another, and the KMS property lets you say exactly which flow is the right one for a given observer without guessing. Ask whether the vacuum restricted to your region behaves as if it were thermal under that region's natural symmetry. And if the answer is yes, you have found your effective clock and your effective temperature. The classic example being an observer undergoing constant acceleration, who finds that the ordinary vacuum is a KMS state with respect to boosts, and therefore perceives a steady bath of quanta at a definite temperature. In this sense, the warmth is not added to the world, it is revealed by the way you slice it. The machinery behind that revelation is called modular theory, and while its full dress is technical, its message fits in a pocket. Given a faithful state on your algebra, there exists a distinguished internal flow, the modular flow, that leaves the state looking balanced, and that plays the role of a canonical time born from the state itself. The generator is sometimes nicknamed a modular Hamiltonian, though it is not usually a simple energy operator, and its orbits are what the thermal time hypothesis points to when it says, "Let the state decide the clock." This is not mysticism, but a precise construction. Pick your algebra and state, build the modular dynamics, and you obtain an arrow along which equilibrium is manifest and departures from equilibrium can be tracked. Remarkably, in certain relativistic settings, the modular flow coincides with geometric motions, boosts for wedge regions, for example, tying the statistical notion of time to space-time symmetries in a way that you can test with detectors. One of the most satisfying cross-checks comes from thermodynamics. A deep theorem shows that the states singled out by the KMS rule are exactly those from which no work can be extracted by any cyclic process that starts and ends with the same Hamiltonian, no matter how clever your control is. So the statistical definition and the second law share a spine. Seen operationally, this means that if your correlations obey the KMS pattern, you are already at the boundary beyond which engines cannot do better on average, and any attempt to push will only rearrange where heat is dumped rather than peel off network. The arrow of time is hiding in that passivity. Processes that violate it on paper cannot be powered by the state in the lab, and the algebraic condition tells you in advance which cycles are doomed to break even. Quantum field theory adds further texture that ordinary many-body systems do not. The local algebras associated with finite regions are of a wild type that forbids a simple, finite counting of microstates. Yet the KMS condition still makes sense and still certifies equilibrium relative to a chosen flow. This saves you when a global Gibbs ensemble cannot be written or would diverge. And it justifies why detectors confined to a region can consistently speak about temperature, even if the universe at large refuses simple bookkeeping. In practice, it lets you argue about thermal features of horizons, stationary spacetimes, and steady flows without pinning everything on a global energy that may not be well defined. From a metrological angle, the payoff is practical. If you are handed an unknown state in a complicated device, say, a quantum simulator with tunable couplings or a field theory in a curved optical medium, you can probe two-point functions along candidate flows and ask which choice makes the KMS relation hold most cleanly. That flow is your thermal time, and the corresponding parameter is your temperature, defined internally rather than imposed. Once you have it, deviations from KMS symmetry become a diagnostic of excitations, gradients, or slow drifts, and you can steer the system back toward balance by shaping the dynamics that define the flow, not by hunting an external clock to blame. In networks of sensors, agreeing on a common KMS frame means sharing the same internal notion of stationarity, which often yields stabler synchronization than trying to coerce many devices into obeying an external tick that their environments do not respect. None of this says that every system carries a single honest thermal time at all moments. Far from equilibrium, you may find a patchwork of approximately KMS sectors, each with its own effective flow and scale, and part of the craft is learning which observables live in which sector and over what windows. Heating, driving, and measurement all deform the algebraic balance, and the KMS diagnostic tells you exactly how they do so by the way correlation functions stop obeying the swap and shift rule. You can leverage that sensitivity to map internal gradients and to decide where to coarse grain, a decision that becomes less arbitrary when guided by where KMS nearly holds. If you want a clean mental summary, keep this. In the algebraic approach, you do not assume time, you infer it. You do not assume temperature, you read it off the ratio of forward to backward fluctuations, and you do not assume the shape of equilibrium. You let the state itself select the flow under which equilibrium is the right word. KMS states are the fixed points of that logic, the places where the world's internal ledger is balanced so perfectly that no engine can profit and no clock outside the state can do better at keeping track. When you look at them this way, thermal time is not an add-on to quantum field theory, but a native feature, an invitation to think of dynamics as a relation between what you can measure and the symmetries of the state you actually have. And the soft closing insight is this: the deeper your description, the less you need extraneous scaffolding. In a good laboratory and in a good theory, the flow that matters is the one the system already writes into its own correlations. And learning to read that script is how you anchor now, without begging for a clock that was never there. Pauli's theorem, where's the time operator? You open a quantum book looking for a neat knob labeled time, the way there's one for position or spin, and you discover an unsettling absence. There is no universal time operator that plays the same role as those familiar observables, and the reason traces back to a careful argument often called Pauli's theorem, which says, roughly but powerfully, that if you tried to build a single, self-adjoint time operator that was perfectly conjugate to energy in the same way position is to momentum, you would be forced into a world where energy stretches without a flaw in both directions. Because real systems have ground states, and stability demands a bottom to the energy spectrum, that universal operator cannot exist. And so time, in the standard formulation, lives as a parameter that drives change rather than a quantity you read off with one sharp measurement. Before you decide that this kills any hope of measuring time in quantum mechanics, slow down and look carefully at what the theorem actually forbids and what it leaves open, because the details are the difference between a dead end and a useful map. The core of the argument is simple to grasp without algebra. A perfectly conjugate pair has a very tight relationship. Shifting one by an amount corresponds to applying a sum transformation generated by the other. And if a true time operator of that kind existed for a system with a lowest possible energy, you could use it to slide the energy down without limit, contradicting the existence of a ground state. The theorem is about that exact, everywhere defined relationship and about an operator with the strongest mathematical properties physicists like self-adjointness. So it does not say no time. Quantities are measurable. It says you cannot have a single global time operator that does everything for every system with a stable energy floor. Once you see the scope, a landscape of honest alternatives opens. One path is to accept that time observables should be represented not by a single sharp operator but by a more general measurement description, what modern theory calls a positive operator valued measure, which is a fancy way of saying you can define a consistent probability distribution for times of events without demanding the strict conditions that triggered Pauli's no-go. This approach covers real laboratory tasks. The time a particle arrives at a detector, the time a metastable state decays, the distribution of waiting times between jumps in a driven atom, or the moment a photon clicks at a sensor after traveling through a device. In each case, you can model the apparatus and derive a time of event distribution that is testable and often beautifully accurate, even though no single universal operator lurks behind it. A second path is to relax the demand that the time generator be self-adjoint and allow a closely related, still well-behaved object that is symmetric but not extendable to full self-adjointness. These maximally symmetric constructions can capture aspects of arrival time for a free particle on the line, for example, and while they do not give you all the mathematical perks of a textbook observable, they give you concrete predictions you can compare with experiments, which is what matters when you are counting clicks. A third path is to notice that the obstruction applies to global, one-size-fits-all time, while many useful systems are periodic. In a ring-like setting, think of a rotor or a clock hand going around. You can define a phase-like quantity that plays the role of time modulo a period, and that object can be represented by an operator on a well-chosen finite space. You do not get an unwrapped infinite timeline, but you do get a meaningful, when in the cycle, observable that instruments can read out and protocols in quantum control and sensing exploit exactly that. Yet another, conceptually different route is to embed your target system inside a larger one that includes a physical clock. You give part of your device the job of being the timekeeper, an oscillator, a spin precessing in a field, an atom with two levels acquiring phase, and you describe the rest of the system conditionally on what the clock reads. In such clock plus system models, time becomes a relational variable, the value you infer from correlations, and you can formalize this idea to show how ordinary dynamics emerges as a statement about conditional probabilities, all without introducing a forbidden universal time operator. When you run this program, the measurable time is as real as any other record in physics. It is written into the joint state of clock and system, and the accuracy you achieve depends on how stable and readable your chosen clock is, not on the existence of a perfect operator living in the abstract. It is also useful to distinguish event times from durations, because they pose different questions. The time a particle exits a trap or arrives at a screen is an event, while how long it lingered in a region during tunneling is a duration. The latter has spawned multiple operational definitions: dwell time, traversal time, values inferred from weak measurements, and each corresponds to a different experimental protocol. You cannot demand that all these notions collapse to a single number, any more than you can demand a single temperature describe a strongly driven, non-equilibrium system. But once you tie the definition to a clear procedure, you can calculate and test it without violating the constraints Pauli identified. The same clarity helps with energy-time talk. It is tempting to announce a universal uncertainty principle that mirrors the position-momentum story, and then infer that measuring energy quickly is impossible. But the careful version is subtler and kinder. There is no general theorem that limits the precision of an energy measurement by the clock time you spend. And indeed, you can measure the energy of a system prepared in a true energy eigenstate as sharply as your apparatus allows. What is limited is how fast states can evolve, how broad in energy a short pulse must be, or how lifetimes imprint widths on spectral lines. Those are clean statements once your question is well framed, and they play nicely with the absence of a universal time operator because they do not require one. Returning to Pauli's message with this map in hand, you can now see its constructive lesson. When you ask about time in quantum mechanics, specify the job you need done, the arrival of a click, the phase of a stable oscillator, the delay through a device, the schedule that aligns two distant labs, and then pick the representation that suits that job rather than demanding a single object that cannot exist. If your system has a ground state and you insist on a globally conjugate, self-adjoint time operator, you will fail. If you allow the richer language of measurements, relational clocks, periodic observables, or context-specific constructions, you will succeed and you will make predictions that match the world. The philosophical moral is soft but firm. Time in quantum theory is not a single needle that swings on every dial. It is a family of honest readouts tied to how you interrogate a system and to what you call an event. And the theorem that seems to withhold a gift is, in practice, a reminder to ask better questions. In the end, you do not lose time. You learn to bring your own. And when you do, the systems you study will tell you when, with all the fidelity your chosen clock can afford, no less, and importantly, no more. Loschmidt echoes, how reversible are we? Try pressing rewind on the universe, even for a heartbeat, and ask whether the film runs backward cleanly. The laboratory version of that daring question is the Loschmidt echo, a protocol that prepares a quantum state, lets it evolve forward for a time, flips the sign of the dynamics as perfectly as technology allows, and evolves for the same time again, finally comparing how closely the return matches the starting point, a single number between 0 and 1 that says how reversible you really were. In a world of exact equations, that number would come back as 1 every time. But in the world you actually inhabit small mismatches, tiny stray couplings, and unmodeled influences nudge the backward journey off the thread of the forward one, so that the echo arrives dimmer than it left. And the way it fades is a fingerprint of what kind of system you are dealing with and how the surrounding stage participates. The idea is older than it sounds and broader than one field. In nuclear magnetic resonance, Hahn's spin echo showed you could refocus a forest of misaligned spins with a clever pulse. proving that many apparent dephasings were not true irreversibilities but timing errors you could cancel. The Loschmidt echo is a sterner test because it attempts a reversal of the full internal script, not just a tidy rotation, and so its success or failure reports on the very possibility of undoing motion rather than merely rephasing it. The recipe is simple to narrate and devilish to implement. Prepare a state you can recognize, drive it under your chosen interactions for a duration, apply a mirror operation that turns the effective generator of change into its negative by inverting magnetic fields, flipping the sign of interactions with a Feshbach knob in cold atoms, reversing gate sequences in a superconducting circuit or trapped ion chain, or swapping the roles of optical elements so phases accrue with opposite sign, and then run the clock for the same interval and measure the overlap with where you began. If your hardware and modeling were perfect, the echo would blaze. But in practice, it decays in patterns that carry genuine physics. In single particle systems, whose classical cousins are chaotic, the overlap often drops rapidly, at a rate tied to how fast nearby trajectories diverge. In integrable settings with many conserved patterns, it ebbs more gently, showing that order in the equations buys you breathing room. In many body systems, the story sharpens because local imperfections are not local for long. Interactions cause them to spread and mingle, so that errors made in a corner echo across the whole, and the return fades faster as the system size grows, which is why macroscopic reversals remain a dream, even if the microscopic rules look reversible on paper. Field by field, the same lesson repeats with its own accent. Ultra-cold gases can reverse interaction signs and watch density ripples attempt a homecoming, revealing how collisions and residual inhomogeneities spoil the march. Cavity and circuit platforms can invert carefully designed gate sets and read out an echo that tracks how accurately the sequence was executed and how strongly the device talked to uncontrolled modes. Spin chains probed in solids let you witness how static disorder or long-range couplings slow or accelerate the loss of return. Across all of them, small, honest differences between the forward and backward scripts loom large because the mismatch is multiplied at every step. That sensitivity is not a flaw, but a feature. The decay of the Loschmidt echo is a diagnostic you can steer, tune the strength of an intentional imperfection, and you move from a regime where the return rate is set by your perturbation to one where it is set by the system's own tendency to mix information, letting you measure, in operational terms, how scrambly your dynamics are. Restrict interactions or add constraints and you can trap information so that the echo lingers, a hallmark of systems that fail to thermalize quickly. Introduce periodic driving, and you may see plateaus where the return holds for surprisingly long stretches before giving way, a signature of pre-thermal organization. Push into strongly disordered territory and the decay may turn painfully slow, hinting at many body localization. These differences are not mere taxonomy. They set your expectations for how long a device can faithfully emulate a model and whether errors will remain tame or amplify. The echo also disentangles culprits you often blend. By designing the reversal so that internal dynamics are inverted while couplings to the outside world are not, you can separate faults of control from genuine leakage of information. If the return fades even when the mirror is polished, you have learned that the system shared details with its environment that no reversal inside the box can retrieve. Because those details now live in correlations you did not invert. As a metrological tool, this is gold. It gives you a way to quantify how many partners were listening, what frequency bands of noise mattered, and where to invest effort in shielding or in smarter compensation rather than in brute force power. Because the echo is an operational test, it feeds engineering directly. You can calibrate pulse shapes by maximizing return. You can benchmark a quantum simulator by how deep an evolution you can reverse before the overlap drops below a target. And you can design error mitigation strategies that preempt the most damaging error channels identified by echo decay. Even partial echoes, where you invert only a subset of terms, map how errors flow through a Hamiltonian the way dye traces currents in a river, which is invaluable when you are debugging a many-component device that will not tell you its secrets any other way. There are subtleties worth savoring. Finite systems often exhibit revivals, moments when the overlap rises again because the discrete spectrum beats back into phase, reminding you that not all decay is final. Echo overshoots can appear when the backward path is a little too strong or too long, a sign that your mirror added its own flourish. and in platforms with long-range couplings. The rate at which the return vanishes can depend more on network geometry than on the microscopic details, inviting you to shape connectivity itself as a control knob for reversibility. All of this brings you to the philosophical heart of the matter with your feet still on the floor. The arrow of time you feel is not contradicted by the existence of microscopic reversals. It is explained by how demanding they are. For small, quiet systems with carefully inverted scripts and obedient environments, you can indeed send a packet of motion back home, and that success is a proof that the rules allow it. But as systems grow, the precision required to undo every tiny nudge grows faster still, and the number of ways the world can hide what you need to know explodes. So the practical result is a one-way street, even though the signposts in the equations do not point. The Loschmidt echo is the calmest way to see that paradox dissolve. You do not argue about principles. You attempt a return and watch the degree of success turn into a number, and that number teaches you how much of your past is within reach. Perhaps that is the quiet human echo to carry with you. Reversibility is real but conditional, made of care and scale and attention. You cannot unscramble an omelette, but you can recover a lost chord if you catch it before the room learns it too well. And you can design your instruments and your habits to keep the path home open a little longer, not by denying the arrow, but by understanding what, in detail, makes it point. Dephasing, how environments blur moments. You think stillness guarantees clarity, but in quantum systems, the quietest moments are often where the blur begins. Because dephasing is what happens when a system keeps its energy, yet loses its sense of direction in phase. Its inner clock hand keeps turning, but tiny, wandering tugs from the surroundings make different copies of that handpoint slightly elsewhere each time you look. So the sharp rhythm that once let you predict outcomes gives way to a soft average. Start with the plain distinction. Relaxation changes populations by letting energy leak to the environment, while dephasing scrambles relative phases without necessarily moving energy at all. And the latter is why an ensemble that began in step ends up speaking over itself, even if no single member fell asleep. You feel it in the lab as a broadening of spectral lines, a fading of interference contrast, a loss of visibility in Ramsey fringes, or a clock whose once razor tick swells into a thicker note, and the culprits wear many everyday faces. Magnetic fields that drift with temperature, fluctuating charges that shuffle in nearby materials, phonons jostling lattices, colliding atoms in a vapor, slow mechanical creep that bends an optical path by a whisper, or even your own probe whose shot noise jitters a level spacing through tiny momentary light shifts. If the disturbances are slow compared to your experiment, each run experiences a slightly different offset, so repeating the sequence and averaging washes out the phase you cared about, even though every single trial looked clean. A phenomenon sometimes called inhomogeneous broadening. If the disturbances are fast, they nudge the phase while you watch, and the blur builds within a single run, smearing your distribution in real time. And in the delicate middle live-colored noise processes, like the famous low-frequency wander that plagues electronics, whose long memory leaves fingerprints that do not fade with simple waiting. The mechanism is not mystical, and you can hold it with a single picture. A quantum superposition is a promise to interfere later, but that promise depends on two alternatives remaining indistinguishable to the rest of the world. The moment the environment learns even a hint about which way the system leaned, through a fluctuating field that couples slightly differently to the two components, through a phonon that remembers a phase, through a nearby spin bath that tilts one path more than the other. The phases that once combined to give a bright result no longer meet in perfect register, and the interference diminishes. Notice that no grand collapse needs to be invoked here, only ordinary entanglement with degrees of freedom you do not track, which is why the best cure sometimes is not stronger isolation, but smarter bookkeeping. If your environment merely shifts the phase slowly, you can refocus by reversing the sign of evolution midstream so that static errors unwind. Or you can tailor a sequence of gentle kicks that cancel the influence of a known band of frequencies while leaving the signal untouched, an approach that turns control pulses into filters whose notches you position to carve away the noise your hardware cannot avoid. Done well, this does not violate any principle. It simply exploits the fact that dephasing is about correlation with stuff you ignore, and you can arrange not to build those correlations in the first place. Different platforms teach the same lesson with different accents. In solid-state qubits, A central spin or charge sits in a bath of many slow neighbors, nuclear spins or two-level defects, whose collective field jitters the qubit's phase unless you tame it with isotopic purification, operate at bias points where first-order sensitivity to noise vanishes, or periodically flip the qubit to average the bath's effect to near zero. In trapped ion and neutral atom systems, stray light shifts and ambient fields cause the internal tick to wander until you stabilize intensities, cancel gradients, and choose magic configurations where the two levels sense the trap equally. In superconducting circuits, flickers of flux and charge push the phase around unless you shape materials, shield carefully, and design transitions whose slopes against those parameters flatten at your chosen operating point. In atomic vapors and molecular beams, collisions and wall interactions randomize phase unless you reduce density or give atoms a protected path. And in photonics, dispersion and path length noise translate vibrations into phase fog unless you actively stabilize interferometers or move the information into formats, like carefully chosen time bins that are less vulnerable to the particular wander your channel suffers. The statistics of the noise matter as much as its magnitude. Fast jitter can average itself away, a counterintuitive relief called narrowing, while very slow drifts turn each run into a slightly different experiment that no amount of naive averaging will fix. Learning which regime you occupy is why teams map noise spectra rather than quoting a single coherence time, and it is why they design their sequences to suppress the frequencies that actually bite. There is no point in fighting a dragon that never visits your village. Measurement itself can be a surprisingly loud neighbor. Detectors that sit too close can imprint random phase shifts through back-action. Probe fields with imperfect intensity control can wobble the energy gap they are meant to read. And feedback loops that chase drift too aggressively can inject their own noise. Honest designs admit this and separate readout windows from evolution windows. Or they spread the measurement over many weak touches that reveal a mean without letting any single poke dominate the phase ledger. Because dephasing is the tax you pay for not tracking the environment, you can also choose to pay in a different currency by moving the coherence into degrees of freedom that couples less strongly to the world, or by encoding information in protected patterns where the environment's most common tugs nudge all components equally and therefore cancel, a strategy that ranges from decoherence-free subspaces in multi-qubit devices to symmetry-protected transitions in precision spectroscopy. The consequences for timing and sensing are direct. The narrower your line, the longer you can wait and still tell phase from noise. The more you suppress dephasing in the band where your signal lives, the faster you can accumulate useful information per unit time. The better you understand which parts of your world are eavesdropping, the more honestly you can claim stability, rather than mistaking mercy from the environment for genuine robustness. There are also telling edge cases that sharpen intuition. Deliberately coupling a system to a fast, featureless bath can sometimes reduce dephasing from slow wander by averaging out the most damaging drifts, an engineered calm that trades one kind of noise for another you can handle. Periodic driving can create sweet spots where the effective sensitivity to certain fluctuations vanishes, buying clean phase in slices of time, and rare regimes with disorder so strong that motion freezes can preserve phase locally at the cost of making the system less responsive. A reminder that less dephasing is not always the same as better for your task. If you want a diagnostic that goes beyond folklore, track not just how visibility decays, but how it decays under different refocusing patterns and weighting schedules. The way those curves change is a fingerprint of the noise spectrum, and fitting them turns guesswork into numbers you can design against. Numbers that tell you whether to invest in materials, in shielding, in control sequences, or in moving the information elsewhere. The soft, closing truth is that dephasing is not a moral failure of quantum systems. It is a description of how the world keeps books on correlations you did not intend to write. If you protect the moments you care about, by staying near operating points the world can't easily shake, by timing your interactions so that unwelcome tugs cancel themselves, by choosing carriers and encodings that are deaf to the loudest parts of your surroundings, the blur recedes and the rhythm returns, and there is a human echo in that craft. Clarity in your own day rarely comes from total isolation. It comes from knowing which influences to average away, which to cancel with symmetry, and which to invite because they carry the signal you sought. so that the moments you wanted to keep do not smear into a haze but remain legible, steady enough to teach you something true before the world's ordinary motions have their say. Recoherence. Can lost time come back? You are told that once a quantum rhythm blurs, it is gone for good. Yet a more careful look shows a quieter truth. Under the right conditions, the lost beat can return, sometimes by design and sometimes on its own. And that return, recoherence, is not magic but bookkeeping. The recovery of phase relationships that were hidden rather than destroyed. To understand when this can happen, begin with a simple promise a superposition makes. If the relative phase between its parts remains well defined, it will later produce interference you can predict. But if that phase becomes dispersed into many slightly different values across unseen degrees of freedom, your averages lose contrast and the pattern fades. Recoherence is what happens when those scattered phase contributions realign, either because the system's internal spectrum forces them to rephase at specific moments, or because you intervene so that earlier disturbances cancel each other, or because the environment itself has a memory and hands information back. The cleanest natural example comes from discrete spectra, an atom interacting with a field mode, or a cloud of ultracold atoms, confined in an optical lattice, can show collapse and revival, where fast incommensurate phase winds initially scramble a visible oscillation, and then, at a predictable later time, many of those winds nearly agree again, so the oscillation reappears. No new energy flows in. You simply wait for the arithmetic of frequencies to line up. Similar revivals show up in trapped ions, where motional and internal degrees of freedom temporarily part ways and then meet again on schedule. And in certain driven many-body systems, where special measure zero patterns, sometimes called scars, guide the dynamics back to a recognizable configuration far more often than a fully thermal picture would suggest. A second route to recoherence uses memory in the surroundings. If the environment is structured rather than featureless, think of a tailored electromagnetic reservoir with a sharp band edge, or a compact spin bath, whose constituents precess at well defined rates. The information that leaked out does not vanish into an infinite sea, but sloshes back with a characteristic delay, producing oscillations and revivals in visibility, as if the system were breathing with its neighbor. In solids, for instance, the slow precession of nearby nuclear spins can periodically refocus a central electronic spin's phase. And in engineered photonic media, reflections and spectral bottlenecks can return amplitude with a well-timed phase, making interference brighten after a lull. You can also make recoherence on purpose by arranging for earlier phase errors to unwind. Carefully timed control pulses flip sensitivities, so that static or slowly varying shifts accrued in the first interval are reversed in the second. And by shaping those pulses to target the actual noise spectrum your hardware faces, you turn control into a tunable filter that opens windows where coherence is effectively restored. This is not mere rephasing of a single variable, but the deliberate design of intervals in which the environment's most damaging tugs cancel themselves, creating pockets of clarity you can use to compare phases, count cycles, or finish a delicate gate. A different, conceptually striking strategy is to erase information that would have revealed which alternative a system took. If path labels are removed so that alternatives become indistinguishable again, interference strength can return even after a detector has peaked, as long as the peak did not irreversibly broadcast the telltale clue to the wider world. And at a higher layer of abstraction, quantum error correction achieves a powerful form of recoherence by encoding logical states across many physical carriers, so that local phase slips can be diagnosed and reversed. What looks lost at the level of 1 qubit can be recovered at the level that actually matters for computation, demonstrating that coherence can be conserved in the right degrees of freedom, even while it appears to decay in the wrong ones. These roots share a unifying message. Coherence is not a substance that evaporates. It is a relation that can migrate. When you lose it from a subsystem, that coherence often resides in correlations with something else. and if you can control or effectively invert the flow that created those correlations, or let a structured world hand them back, you can draw the relation home. The limits are real, and they keep the story honest. If information has dispersed into too many uncontrolled channels, with a broad spread of delays, the fine timing required for a clean return becomes impractical. If the process that created the blur was accompanied by genuine energy exchange and heating, you cannot unspend that cost without doing additional work elsewhere. And if the environment has no memory, its fluctuations are too fast and too featureless, then no echo of your earlier phase survives for you to reclaim. And the best you can do is prevent further loss, rather than reverse what is gone. In the laboratory, you diagnose and exploit recoherence by watching not just how visibility decays, but how it responds to weighting, to pulses, and to changes in the spectral landscape. A revival at a predictable delay marks a discrete set of frequencies conspiring to align oscillations that follow the period of a nearby bath, tell you who is carrying your information. A recovery that appears only under a specific sequence reveals the bandwidth of the noise you cancelled and the part of the signal you preserved. With those fingerprints in hand, you decide whether to shape reservoirs, to encourage returns, to choose carriers that naturally experience revivals, to schedule operations to land on recoherence peaks, or to encode information so that what must be preserved lives at a level where your controls can actually act. There is a gentle practical payoff to this view. In timing and sensing, well-timed recoherence windows let you compare phases over longer baselines than a raw coherence time suggests, boosting sensitivity without brute force power in simulation. Revivals serve as beacons that validate 8 models of interaction and reveal whether your hardware is truly exploring the intended dynamics or quietly leaking into an unintended sector. In communication, protocols that anticipate environmental memory can schedule readouts to catch returning amplitude rather than treat every delay as loss. And in computing, cycles of encode, evolve, reconstruct make clear that decoherence is not the end of the story if the right checks and symmetries are in place. The soft closing thought is that lost time in quantum experiments is often time whose record has been misfiled rather than burned. When you learn where the record went, to sidebands, to neighbors, to a structured bath, to the code space of a wider system, you gain options for bringing it back, not by defying the arrow of thermodynamic, but by tracing the ledger with enough care to reverse the entries that were only provisional. And even when full restoration is impossible, the attempt teaches you which parts of your world keep faith with your phase, and which parts do not. So you can stage your next measurement in a place where, for a precious interval, the rhythm returns, and the story finishes the sentence it began. Recurrence times in finite quantum worlds. You spend most days assuming that once a system settles into its routine, it will never stumble back to the exact arrangement it had before. Yet in a finite quantum world, there is a quieter promise tucked into the spectrum. If the list of allowed energies is discrete, and the dynamics are left undisturbed, the phases that weave those energies together must, sooner or later, nearly realign. And when they do, the state returns astonishingly close to where it began. This is the recurrence. A patient reunion written into the arithmetic of frequencies, rather than the push of any external hand, to feel the mechanism without symbols. Imagine your state as a chord played on many strings at once, each string humming with its own pure note, set by an allowed energy, and the total sound changing because the notes drift in and out of step. If the notes are perfectly commensurate, there is a common beat and the chord repeats exactly after a period you could, in principle, calculate. But if the notes are merely almost commensurate, as they are in most interesting systems, the alignment is not perfect yet still becomes arbitrarily close given enough time. And the enough can be so stupendously large that for all practical purposes, you would have grown old before the echo returns. This is the crux. Recurrence is guaranteed by discreteness and isolation, but the time scale is set by the least common rhythm of many incommensurate tones, which tends to explode with system size and complexity. Concrete pictures help. A particle trapped on a finite ring explores positions in a way that never truly forgets its starting shape. A quantum walk on a small graph reweaves amplitude along edges until the initial pattern reappears with striking fidelity. A few interacting spins, evo, leave through a finite set of relative phases, and, after a long algorithmic march, revisit their launch point. In each case, there was no thermostat, no external driving, only the quiet bookkeeping of a finite Hilbert space, ensuring that the list of phases never spreads out onto a continuum, enlarge the system, or couple it, even weakly, to a broad environment. And the spectrum densifies until the common beat retreats beyond any credible horizon, which is why recurrence lives as a theorem in math, but a rumor in macroscopic life. The distinction between exact and almost recurrences matters for what you can claim. If degeneracies and simple ratios rule your spectrum, returns can be sharp and regular, a clean periodicity you can plan around. If the ratios are irrational mixtures, the path winds through a high-dimensional torus of phases and only stum. Near its starting point after astronomically many cycles, producing revivals that are good enough to measure in small devices yet, that smear into irrelevance as the number of degrees of freedom grows. This is not a trick of notation, but an honest statement about how many independent clocks you let into the room. Few clocks, frequent meetings, many clocks, rare coincidences. Recurrence is also not the same as reversibility. Reversibility asks whether you could, by flipping the dynamics, drive the system back on command. Recurrence asks whether, by sheer passage of internal time, the system will wander back on its own. You can have one without the other, and experiments that chase reversals with engineered pulses are a different game from those that simply wait and watch for a spontaneous return. Indeed, in a strict sense, equilibration in a closed finite system is always temporary. Local observables grow typical for long stretches. But given a patience bordering on myth, those observables will meander back toward their initial values, and then away again, and the arrow you feel is the ratio of how long you'd have to wait for such a near miss to occur to how quickly ordinary mixing drives you toward the typical. With a handful of qubits you can observe the dance directly, while with a mole of atoms the waiting time beats the lifetime of stars. So the theorem stays true, and the world remains indifferent to it. There are edges to this story that deepen it rather than dilute it. Constraints and conserved quantities can make returns more visible by pruning the list of active notes, which is why certain carefully prepared patterns in many body systems, special non-ergodic states, sometimes called scars, revisit their origins far more often than generic ones, and why finite-size integrable models can exhibit crisp recurrences that vanish when you nudge them toward chaos. Disorder can slow the spread of information so thoroughly that portions of a system retain memory for surprisingly long windows, edging you closer to a revival even without fine-tuning. Symmetry can herd phases into families that march together and meet more readily, yet none of these rescues macroscopic reality from the central arithmetic. Each extra independent frequency multiplies the common period until it outruns any sensible clock you could build. From the vantage of design and measurement, recurrence becomes a tool rather than only a curiosity in small quantum simulators. You can benchmark whether your model has the right spectrum by checking that predicted near returns occur at the right delays. In sensing, if a platform has natural revivals, you can sched Yule redouts to land on those peaks and recover contrast that would otherwise appear lost. In communication channels that are effectively finite, waveguide loops, resonators with a handful of modes, you can anticipate re-emergent signals that would look like noise in a continuum, and instead harvest them. And in error diagnosis, the absence or mistiming of expected revivals announces unwanted couplings or drift in parameters you thought were fixed. But honesty matters. Genuine coupling to a large environment turns the discrete hum into a blur, and energy exchange replaces the tidy dance of phases with real loss that no weighting can undo, even without a bath. Coarse graining, your deliberate choice to look only at a subpart. makes recurrences invisible, because the information needed to recognize the original pattern now lives in correlations you refuse to track. In both cases, the right moral is not that recurrence was a lie, but that you changed the question to one for which recurrence no longer speaks. If there is a human echo here, it is this. In small, well-kept worlds, patterns do find their way home given a patience matched to their size. As worlds grow and their lists of rhythms lengthen, the same promise recedes into the kind of future you cannot practically reach. Not because the rules are different, but because coincidence becomes too rare to count on. Learning to spot which world you inhabit, how many clocks you invited, how isolated they are, how coarse your gaze will be, teaches you when to plan for a return and when to trust the typical. And it softens the paradox between a universe that allows everything in principle and a life that only ever sees some things in practice. Page curve, time and black hole information. Imagine watching a campfire that seems to burn memories. Instead of wood, the sparks flying off as tiny featureless embers, and being told that if you were infinitely patient and impossibly careful, you could reconstruct the first song ever sung around that fire from the glow alone. That is the promise hidden in the page curve, a simple sketch that reframes the black hole information puzzle as a story about how quantum correlations flow in time. And it asks you to unlearn the early lesson that Hawking radiation is just thermal, and therefore forgetful. Because if the universe truly evolves without losing information, then the fine-grained entropy of the radiation must first rise, and then fall back to zero by the end of evaporation. Tracing a hill whose crest is the page time, the moment when the outgoing light begins to carry away not only energy but also the detailed pattern of what fell in. Start gently with the players. A black hole forms from ordinary matter in a pure quantum state. Semi-classical reasoning says it emits radiation with a spectrum that looks perfectly thermal, like a hot coal. And if you naively add up that radiation's entropy, using only local temperature, you watch a monotonic climb. More and more ignorance with every photon, until nothing remains but a fog of featureless heat and an accounting error that offends unitarity. Don Page's insight was to stop treating the radiation as a pile of independent embers and instead treat the entire situation as a bipartite quantum system that scrambles information internally and then lever cacks quanta to the outside. A perspective that comes with a crisp prediction. For a generic, efficient scrambler, the entanglement between the whole and its radiation grows like a balloon at first, because early light must be entangled with the heavy object that still holds most of the degrees of freedom. But once roughly half the total entropy has been radiated, the logic reverses. New emissions are more likely to be correlated with a cloud already outside than with a shrinking remnant. So the radiation's fine-grained entropy starts to drop. And by the time evaporation completes, the outside is again pure, encoded not locally in any one photon, but globally across their joint state. The middle of the story is where modern gravity learned to speak quantum bookkeeping more fluently. For years, the stumbling block was that semi-classical calculations seemed to force the always rising curve, because they computed the entropy of the radiation by tracing over everything behind the horizon, with no channel for information to escape, except the thermal flux. The recent turn came from tools that marry quantum field theory with the minimal area logic of holography, introducing quantum extremal surfaces and the island rule, which in plain language says that when you compute the fine-grained entropy of the radiation, you may, after a certain time, need to include a region inside the black hole. In the radiation's entanglement wedge, the outside observer, in an information theoretic sense, owns that island. This sounds like a trick until you look at what it accomplishes. Before the page time, the best surface that bounds the radiation's entropy sits outside and the entropy rises. As Hawking taught, after the page time, the best surface jumps to one that cuts off an interior island, and the formula returns an entropy that falls. Exactly the page curve shape demanded by unitary evolution. The deep point is not that we are peeking behind the curtain, but that the correct, fine-grained notion of what the outside can decode changes in time and is consistent with quantum mechanics once you account for subtle state dependent saddles in the gravitational path integral, often visualized as replica wormholes in technical papers. But operationally, just a reminder that correlations can bend the geometry of entanglement, as seen by different observers. With that curve drawn, you can ask sharper questions that do not require mystical language. How fast does a black hole scramble new infalling information? Results suggest it is among nature's quickest mixers, so that after a short scrambling time, the content of what fell in is thoroughly diffused over the hole's degrees of freedom. How soon after the page time could an ideal decoder, armed with enough of the radiation, reconstruct an infalling message? The Hayden-Fapreskill thought experiment answers surprisingly quickly, provided you have captured more than half of the total output, and you wield a decoder of heroic power. Does any of this let you signal from inside the hole to the outside? No. The curve certifies recoverability in principle, without giving you a channel that defeats causal structure. Because the needed decoding is a global, computationally enormous operation on many quanta collected over long times, not a local knob you could twist in real time at the horizon. The educational turn is to separate coarse, grained and fine-grained torque. The Hawking temperature and the area law still organize the average flux, and the thermodynamic bookkeeping. You can predict power output, lifetimes, and equilibria using those, while the page curve governs the hidden order in the joint state. Both can be true at once. Every small handful of photons looks thermal when tested locally, yet the full cloud carries a vast, delicate pattern of correlations that only an enormous, globally coherent measurement could read. This is the same separation that lets a warm room look random in any small corner, while still encoding detailed information in the long-range correlations of its microscopic state. The curve also tames older puzzles without grand pronouncements. If you feared that late radiation must be simultaneously entangled with both the early radiation and the interior partner of its Hawking mode, a conflict that fueled firewall debates, the island perspective tells you that interior partner is not an independent degree of freedom for the outside observer past the page time. The entanglement wedge of the radiation includes an island that accounts for those modes. So the monogamy crisis evaporates when you phrase it in the right variables. If you worried that unitary recovery demands visible violations of semi-classical physics at the horizon, the modern view says the semi-classical picture remains an excellent local approximation, while the global accounting of entropy uses non-perturbative saddles that are invisible to any single detector, but decisive for the full state. There are boundaries worth respecting. The page curve is a statement about fine-grained entropy in idealized settings, where gravitational back reaction and quantum fields are treated with care. In realistic astrophysical environments, accretion, rotation, charge, and surrounding matter complicate the simple sketch. And even if unitarity is safe, decoding is likely intractable for mortal computers. So the principle that information returns does not hand you a practical black hole hard drive still. The conceptual win is large. You no longer have to choose between a universe that forgets and equations that conserve. You can keep both by admitting that who owns which degrees of freedom is a subtle time-dependent question in gravity. The soft closing thought is that the page curve is not a mere plot tucked in a textbook, but a new way of listening to the universe's most secretive objects. At first, they hum like simple heaters. Then, almost imperceptibly, the melody changes as the chorus of outgoing quanta begins to encode a biography. If you had perfect patience and an impossibly large ear, you could hear not the words themselves, but the certainty that no word was lost, only rewritten across the choir in harmonies too wide for any single voice. And that recognition, quiet, careful, and deeply consistent, teaches you that time near a black hole is not only geometry and not only heat, but also the long arc by which hidden order leaves its most famous hiding place and returns to the world. Holographic time slices and entropy. You can watch a space-time the way you might leaf through a photo album, one slice at a time. And in holography, those time slices are not just a way to organize pictures, but a working tool for reading entropy from geometry. Because a boundary region's entanglement is captured by the area of a special bulk surface that anchors on its edge and dives inward to the slice where that area is smallest. The quiet revelation is that you can pick many different slices, and, if you do the job correctly, you will land on the same answer, since the true surface is not merely minimal on one snapshot, but extremal in the full spacetime, the one that refuses to grow if you nudge it slightly forward or backward. In time, this independence from your favorite foliation is not a mathematical parlor trick. It is the statement that the information a boundary observer can certify about a region at a given time is coded in a piece of the bulk that the observer owns. The entanglement wedge, and that wedge is carved out by those extremal surfaces in a way that respects causality while remaining sensitive to the deep interior. Begin gently by picturing the simplest scene. A calm holographic universe whose boundary is a fixed stage where your field theory lives, and a subregion on that boundary that you choose to study, to ask, how entangled is this region with the rest? You do not count microscopic pairs one by one. You search the bulk for a surface that hangs from the region's perimeter, and has the least area among all candidates that obey the rules. When nothing is changing in time, that surface lies on a single constant time slice, and the prescription feels like a geometrical puzzle with a C-RISP answer. But real states evolve, and then your minimal surface must be allowed to tilt, to cut across slices, to explore the covariant theater of the bulk. Because entropy at time now is not about a still photo of the interior, but about the full set of nearby histories that keep the area stationary. And the surface you find is the one that weaves through that theater without preferring a frame. This shift from minimal on a slice to extremal in space-time does more than keep the bookkeeping honest. It turns quantum inequalities into geometric ones, and back again. Strong subadditivity, an information, theoretic statement that correlations cannot be arranged arbitrarily, becomes a triangle inequality for areas when you compare the right pairs of surfaces. Monotonicity of entropy under inclusion, the fact that a bigger region cannot be less entangled than a smaller one, follows from the way surfaces cannot cross without giving you a cheaper candidate. Even the directionality of certain renormalization flows can be seen in how the areas of appropriate bulk surfaces shrink as you walk from ultraviolet pictures to infrared ones. A geometric witness of degrees of freedom thinning out as you zoom toward longer scales. Time-dependent physics sharpens these correspondences. After a disturbance on the boundary, the extremal surface for a region does not jump discontinuously to a fully grown shape. Rather, it stretches inward with a causal pace, reflecting that information about the quench needs time to percolate through the state, where a naive thermal picture would tell you entropy simply rises with temperature. The covariant geometry teaches you that local bursts, global quenches, and steady drives leave distinct patterns in how surfaces tilt and where they anchor, patterns that you can read off as different temporal profiles of entanglement growth without ever writing a differential equation. Crucially, you cannot cheat the speed limit, no matter how you choose your slice. No surface can probe parts of the bulk that would imply correlations appear outside the domain allowed by boundary causality. And when you try, the extremal condition quietly reroutes your candidate to a legal path, reminding you that who knows what when is encoded in the feasible geometry. At this point, a natural anxiety arises. If different slices are allowed, how do you know you did not miss the true surface by staring at the wrong moment? The cure is a maximin principle. Pick any slice, find the minimal area surface on it, then vary the slice, and keep the one for which that minimal area is as large as possible. The theorem behind the scenes says this maxit min construction equals the covariant extremal surface, an algorithmic comfort that turns a philosophical worry about which time is right into a practical search that works. In laboratories that simulate holographic dynamics with controlled models, numerical explorers follow exactly this playbook, letting them see area jumps that correspond to phase transitions in the dominant surface, and by translation, to sudden reorganizations of entanglement structure in the field theory, clean, testable, and far richer than a single rising curve. The geometry itself can be rephrased in a language that protects your intuition. Instead of surfaces, imagine incompressible flows of bit threads, invisible lines that run through the bulk from the region to its complement, and whose maximum number equals the entropy. On a fixed slice, those threads squeeze E through a narrow throat, the same throat, a minimal surface hugs, while in a time-dependent setting, they can reroute through different throats as slices tilt, giving you a picture of information as a conserved current constrained by bottlenecks. You can see the virtue of this view is that it makes inequalities almost obvious and clarifies why two disjoint regions can suddenly become more than the sum of their parts. When a new thread bundle opens a bulk shortcut between them, a geometric avatar of multipartite entanglement emerging in time. When quantum corrections matter, the rule does not break. It deepens. You replace bare area with a generalized entropy that adds the bulk's own entanglement across the surface to its geometric area, and you extremize that total. This move, modest in wording, braids gravity and quantum matter so tightly that statements about entropy focusing along light-like deformations, constraints that look like refined versions of the second law, become statements about how cross-sectional areas in the bulk are allowed to change. The upshot is that a consistent quantum gravity insists on information, theoretic inequalities that ordinary field theories satisfy only when they are healthy, giving you a surprisingly practical diagnostic if a proposed microscopic model violates those entropic bounds. It cannot have a good holographic dual, because there would be no geometry whose extremal surfaces could obey the corresponding area rules. You might worry that this is all esoteric, yet it gives you concrete handles on problems you actually care about. In strongly coupled systems, where traditional quasi-particles do not exist, time-resolved entanglement cuts, computed from holographic surfaces, predict how quickly disturbances spread and how robustly information is distributed. Numbers you can compare to transport and thermalization measurements. In engineered quantum devices, toy geometries help you reason about how to partition a processor into regions whose cross-talk is minimized in time, translating extremal surface intuition into wiring diagrams and scheduling strategies that keep the bottlenecks where you want them. And in quantum error correction, the entanglement wedge idea clarifies which bulk operators can be reconstructed from which boundary pieces, at which times a practical map for how redundancy protects interior data against localized faults. The softest lesson, saved for the end, is about how you narrate change. Holographic time slices teach you to resist the temptation to fix a frame and force reality to fit it. Instead, you ask which slicing makes the correlations you can verify most transparent. You let geometry tell you where the bottlenecks move as the state evolves, and you accept that the right now is the one that leaves the extremal surface unchanged under the tiniest pushes forward or back. Do this and entropy stops feeling like an abstract statistic and starts feeling like a shape your questions carve out of space-time. A shape that grows or shrinks depending on how you divide the world, that obeys causal traffic laws more faithfully than any slogan, and that, when read carefully, turns the passage of time into a legible sequence of rearrangements rather than a blur. You begin gently by tracing one slice, grow deeper by learning how the true surface threads them all, and close softly with the recognition that in a holographic universe, the most honest measure of how much is often how narrow the throat is, and the most honest measure of when is whichever slice leaves that throat at rest. Modular flow, states generating their own time. You don't need a clock on the wall if the state you hold already knows how it wants to change. And that is the quiet promise of modular flow. Fix a quantum state and a set of observables, and there exists a distinguished internal motion that carries each observable to a new one, while leaving all the expectation values measured in that state unchanged, as if the state itself were laying down train tracks, and the flow were the schedule. You can think of it as a rule that says, slide forward, according to the state's own bookkeeping, not an external tick, frequently non-local, but always the one that makes the state look perfectly balanced while it acts. Start from an operational picture, rather than jargon. Hand yourself a quantum system and a region you can probe, and imagine you could unspool every correlation inside your lab so that you could ask which transformations preserve the state's statistics, yet shuffle where information sits. Among all such relabelings, there is a canonical one that forms a continuous flow. And if you push an observable along this flow for a while and pull it back, the state cannot tell you did anything. Averages do not drift, yet certain combinations of observables do change in ways that reveal structure otherwise hidden. This is what makes modular flow a microscope for entanglement, rather than a mere change of coordinates. It peels apart where information lives without disturbing the ledger that defines equilibrium for the chosen state. In plane settings, this becomes almost geometric. Take a quantum field confined to a half space and measured in its calm vacuum, and the modular flow of that half mirrors. Like boost that leaves the boundary fixed, so points deeper in the region slide along graceful hyperbolas. In scale, invariant theories, intervals and balls enjoy similar luck, with modular motion acting like a symmetrical squeeze that keeps the edges anchored. But move to a generic region or a messy many-body state, and the modular Hamiltonian ceases to be a tidy integral of local densities, and instead becomes an intricate, non-local operator that reaches across the region, pulling and cancelling in a way that cannot be mimicked by a simple field. This difference is not a defect. It is the fingerprint of the correlations that knit the state together. And reading that fingerprint is precisely why the concept is valuable. A pair of practical rules fall out immediately and guide real work. First, small deformations of a reference state change its entropy exactly as if you had measured the change in the modular Hamiltonian. An entanglement first law that trades an unobservable count of hidden microstates for an observable expectation value, turning questions about how much more mixed did my region become into questions about an operate. Or you can, in principle, estimate, second, the object that measures the distance between your actual state and a reconstructed one. The relative entropy decreases when you forget details, and that monotonic drift is equivalent to saying that modular flow defines the natural direction in which information cannot increase if you pass to coarser descriptions, a statement that underwrites the security of error correction and the honesty of thermodynamic arrows at the level of inference. If you prefer circuits over inequalities, modular flow has a concrete face as a recovery tool. Given a noisy channel that erased part of your system, the best map that undoes the damage when the noise is not too strong can be written in terms of the very operators that generate modular motion, meaning that to rewind a mistake, you do not need a perfect time reversal. You need the state's own internal clock. This insight explains why certain encodings are robust, not because they float above noise, but because their modular structure makes the right recovery act, like a natural countercurrent. And it is why prototype experiments in programmable simulators aim to measure modular features indirectly, by comparing expectation values before and after carefully designed deformations that imitate the flow. In strongly coupled systems where particles are the wrong language, modular flow becomes your grammar as a localized disturbance spreads. Observables dragged by the flow reveal which combinations of degrees of freedom are truly tied together, and how quickly, without ever asking the system to cough up a quasi-particle, the speed at which modular, transformed operators start to overlap plays the role of a causal diagnostic, telling you how information routes through the fabric without demanding a simple light cone. And when you couple two regions, the way their modular flows braid or fail to braid exposes whether a sharp boundary between what I can reconstruct and what I cannot exists. A distinction that guides how you partition a processor, where you place sensors, and which interfaces must be kept especially quiet. The same idea threads through holographic duality with a practical twist. For states that admit a clean geometric avatar, the modular flow of a boundary region shadows a corresponding motion in the interior of the dual spacetime. So the operator you can reconstruct from that region at a given $time can be pictured as a bulk excitation moving inside a wedge that the region owns. This is not hand-waving. Reconstruction formulas in that setting are built from kernels that are themselves modular objects. And it explains why some interior data can be recovered from surprisingly small boundary pieces, while other data cannot, not because of mystical non-locality, but because the state's own clock restricts which paths exist that keep the wedge intact. None of this requires you to pretend that modular motion is a conventional time evolution. It need not commute with ordinary dynamics. And in driven devices, the two flows can tug in different directions. The point is that modular flow is the unique state-picked way of sliding that leaves the state steady while exposing structure in the algebra of observables. And that uniqueness is what lets you replace vague appeals to how the system wants to move with a testable prescription. At the edges, the picture becomes even richer. Between two different states, you can define a relative modular flow that measures how one set of correlations must be twisted to look like the other, a tool that quantifies the effort to morph prepared data into a target, and that sharpens intuitions about irreversibility without invoking heat. In families of states, the way modular generators change along the path behaves like a kind of geometric connection, complete with phases that accumulate when you loop, which hints at control strategies where you parallel transport operators to minimize unwanted spreading, a design principle already being explored in small programmable platforms. For experimenters who bristle at abstraction, there are honest footholds, variants of entanglement spectroscopy, randomized measurements, and learning. Base tomography can approximate the action of modular flow on a chosen subset of observables. Quench and probe protocols can watch how modularly transformed operators pick up or shed support, revealing hidden constraints that ordinary correlation functions miss. And in metrology, driving along directions that are modularly quiet. Directions the state regards as neutral lets you extract small signals with less back action because you are not pushing against the state's own balance. The closing lesson, gentle but durable, is that time in a quantum setting is not a single river flowing for all problems. Sometimes you need the river that a Hamiltonian carves, sometimes the calendar set by an external oscillator, and sometimes the private stream that a state defines for itself. Modular flow is that private stream, and when you learn to swim in it, you stop forcing your questions into the wrong current. You begin with the state you actually have. You ask how it wants to slide its own observables. While staying composed, you follow that slide to see which patterns are structural and which are incidental, and you end with a clearer understanding of where information lives and how gently you must touch it to make it speak. The kind of clarity that slows the mind even as it sharpens judgment, and that turns a cryptic phrase like states generating their own time into a working instruction for how to learn from a system without drowning out its voice. Complexity equals time computational arrows. You have felt many arrows by now: thermodynamic, entanglement, modular. And yet there is another, quieter hand that points forward, even when energy is conserved and entropy refuses to budge. The arrow of computational complexity, the simple but stern fact that for a closed quantum system, the number of elementary steps needed to synthesize its exact state from something easy almost always grows with time, then plateaus only after an absurdly long climb, so that how hard it would be to build this state from scratch behaves like a clock you can't easily fool. Begin gently with a picture you can hold. Take n qubits arranged like notes on a staff. Give yourself a fixed set of small local gates, tinny rotations, 2-qubit entanglers, and ask, what is the shortest circuit that takes a simple reference state into the state you actually have? That shortest circuit length is the circuit complexity. And as you let the system evolve under some reasonable Hamiltonian, no heating, no bath, just unitary motion, the minimal number of gates required to recreate its precise wave function typically increases almost linearly for a very long window, because each layer of genuine dynamics weaves new, non-trivial patterns that cannot be undone by a handful of lucky cancellations, even if some observables look settled and entanglement has already spread. The exact microscopic arrangement keeps acquiring structure in a way that makes the optimal recipe longer and longer, a phenomenon you can call a second law of complexity. For most directions you push, complexity wants to rise until it nears a ceiling that is itself enormous, of order the size of the full space of possibilities. You do not need heavy equations to feel why. A small circuit explores a tiny neighborhood in the landscape of all states, and long circuits explore much more of it. Typical time evolution, like a good scrambler, wanders into corners that are combinatorially far from your neat starting point, and the shortest ladder back to that corner lengthens because shortcuts become rare. The chance that a brief, low-depth sequence hits the exact microstructure you now possess is negligibly small. Reversibility is not denied here. If you could perfectly invert every step, you would return. But the point is different. Without a detailed logbook of what you did, the effort to reconstruct the state from an easy seed explodes. So the practical arrow points from simple to build, toward only buildable with great effort. Even in an isolated universe that in principle has no losses. This perspective reaches beyond philosophy when you turn it into design rules. In computation, a low complexity state holds spare uncomplexity, a reserve of simplicity you can spend to perform useful work. Apply clean gates, and you convert that reserve into depth that steers amplitudes where you want them. But let dynamics wander unchecked, or let noise mimic randomness, and you burn the reserve into a highly complex state that becomes a stubborn substrate. Further gates stop accomplishing clean aims without massive overhead. Much like adding neat lines of code to a tangled legacy project yields diminishing returns. The resource theory whispered here is practical. Uncomplexity fuels precise control, and protocols that intentionally reset parts of a register, inject fresh ancillas, or cool subsystems are doing more than housekeeping. They are replenishing the capacity to compute by lowering the minimal circuit burden for the tasks ahead. In physics at strong coupling, where entanglement long ago saturated local patches and thermodynamic descriptors look steady, complexity keeps time when other dials stall. The microstate remains exactly pure but ever harder to synthesize. And in holographic jewels, this relentless growth peaks out as a slow, almost linear deepening of interior geometry. The volume behind a horizon or the action in a particular region offering a poetic but testable link. As the state's gate count climbs, an internal bridge stretches, a translation from more steps to rebuild into more interior to traverse, survives crude perturbations. Drop in a sharp kick, and you see a switchback effect. Apparent progress is briefly undone, like a hiker forced to backtrack along a ridge, before linear growth resumes. A geometric trace of the fact that some parts of your circuit L only after you account for their precise order. None of this demands that you memorize jargon, only that you accept a sober moral. The universe's exact microhistory can remain unitary, and yet its faithful description, in the language of small steps, becomes harder with time, and geometry seems to know. The computational arrow also clarifies puzzles that thermodynamics alone leaves fuzzy. Fine-grained entropy in a closed system stays flat. But your ability to reverse engineer the microstate from modest experiments collapses as complexity rises. Cryptography leans on this difference. Conserving maps can still be effectively one-way if recovering the input requires circuits exponentially longer than producing the output. And pseudo-random states in quantum devices are precisely those that look simple locally, yet require heroic depth to reproduce globally. In error correction, logical information hides in patterns that resist shallow attacks, and decoding requires structured circuits that harvest pockets of remaining uncomplexity before noise inflates them away. Even in metrology, the sweet spot for phase tracking is not maximally tangled and random, but structured enough for sensitivity. simple enough to steer, which is why calibration cycles periodically drain complexity with resets and refills. You might wonder whether this arrow merely rebrands the recurrence story. And the honest answer is that it strengthens it operationally. Exact recurrences exist in finite, isolated worlds. But the time to stumble back scales doubly, astronomical with size. And the complexity ceiling sits just below that unreachable horizon. Long before recurrence, complexity has saturated near its maximum, and wandering within that plateau does not make control easier. It only reshuffles a giant haystack of equally hard to synthesize states. Thus, the computational arrow explains why the return promised by pure mathematics does not help your instruments, and why practical irreversibility can coexist with perfect microscopic bookkeeping. There are caveats worth holding with care. Complexity is basis, and gate set dependent. So you must declare your primitives before you speak. Many tasks do not require exact state synthesis, only approximate control over a few observables. And there, the arrow softens. Clever variational strategies can ride low, dimensional manifolds where useful answers live. Noise itself can sometimes lower apparent complexity by squashing delicate structure, but that is a poisoned gift. You have not gained uncomplexity you can spend. You have lost distinguishability you needed, and claims about fast scramblers or linear growth forever hinge on real dynamics, integrable systems, constrained lattices, and measurement. Heavy circuits carve exceptions, where complexity rises more slowly or oscillates with structure rather than marching relentlessly. Still, the engineering takeaway persists. Budget your depth the way you budget power. Schedule resets that restore uncomplexity before it is gone. Prefer architectures that confine unnecessary scrambling, and measure progress not only by loss functions or fidelities, but by whether the minimal recipes for your intermediate states remain short enough to be steerable. When they do not, you are not merely running out of time. You are running out of simplicity. And the cure is not to shout with more gates, but to clear space, cool, purge, reinitialize. So intention can again move the needle. Perhaps the softest echo is personal. Complexity's arrow says that even in a world where nothing fundamental is lost, your capacity to act with precision depends on the simplicity you preserve. Projects, relationships, and thoughts become hard to steer not only because they are large, but because the minimal steps to reach their exact current form have grown long, and recovery begins by reclaiming uncomplexity. By simplifying the part you own, resetting a register, choosing a smaller subproblem that can be built cleanly, until the path forward becomes a sequence of steps you can actually take. In that sense, complexity equals time is not a slogan to settle an argument, but a lens to help you plan. Treat simplicity as fuel, treat depth as a cost, and let the rise or fall of that cost be the arrow that tells you whether you are moving with or against the grain of your own system. A calm metric that slows your mind even as it sharpens your aim. Cosmological initial conditions and first tick. Set aside the fireworks of the Big Bang and ask a gentler question. When did the universe get its first usable second? The first moment when before and after meant anything more than guesses. And what choices were already baked into that first tick? To reach a careful answer, you start by admitting that time is only as good as the clocks you can build, and clocks need a stage. A smooth spacetime in which light travels reliably and matter fields have well-defined behavior. So the very earliest instants, when quantum gravity turbulence likely made geometry itself fluctuate, were not yet a place where ticking could be agreed upon. The practical flow of cosmic time begins only once the expanding universe can be translated as a nearly uniform medium whose large-scale properties change slowly from one moment to the next. And in cosmology that once is encoded in the scale factor that measures how distances grow, and in a thermal bath whose temperature cools predictably as the whole system dilutes, giving every local observer the same recipe for counting. Follow the expansion, read the temperature, and you have a shared notion of seconds. The unsettling part is that, This calm beginning demanded very special initial conditions. An early universe, astonishingly smooth across regions, that without explanation should never have coordinated, spatially flat to a precision that asks for a mechanism rather than a miracle, and sprinkled with tiny seed regularities of just the right size to later become galaxies, without wrecking uniformity. These traits are not decorative. They define the first page of the cosmic ledger. Uniformity lets you define a cosmic time the same way everywhere. Flatness keeps that time from distorting as you move across vast distances. And small, nearly scale, free ripples give structure a fair start, while leaving the background readable enough to act as a clock. The leading explanation for how such a page was set is inflation, a phase of accelerated expansion that, if it occurred, took a small patch of pre-existing space and stretched it so violently that any initial wrinkles were ironed out, while random quantum jitters in the underlying fields were amplified into the tiny density variations we now map in the microwave sky. This move does three jobs at once that matter for first tick. It explains why distant regions look the same, despite having had no time to talk in a non-inflating universe. It drives the spatial curvature towards zero, so that straight lines remain straight on average, and it sets the statistical pattern of the primordial ripples, which becomes a metronome for later growth. When inflation ends, the energy that powered it decays into a hot, dense soup of particles, in a step called reheating, and from then on the universe behaves like a well-instrumented lab. Expansion cools the plasma, interactions keep matter and radiation in near equilibrium for long intervals, and the clocks you build out of particle interactions, nuclear reactions, or photon scattering would all agree, up to known corrections, on the pace at which events unfold. This is the first tick in any operational sense, the handoff from a speculative prehistory to a domain where seconds can be counted and compared. But initial conditions are not only about geometry and ripples, they carry an arrow. The early cosmos was in an extraordinarily low entropy configuration once you include gravity in the bookkeeping, because a hot, uniform distribution of matter on a vast scale is actually a very special state for a self-gravitating system. Gravity prefers clumps, and the fact that clumps were absent is what allowed entropy to increase as structures formed. That low gravitational entropy is what lets earlier be cleaner than later. And it is as much a part of the first tick as temperature or expansion rate. No lab we build today starts from such a pristine page, which is why the cosmological arrow feels so universal. Countless independent processes, stars igniting, gas cooling, chemistry advancing, inherit their direction from that special smooth beginning. Alternatives to inflation take the question of first tick in different directions, while trying to keep the same observational promises. In bouncing models, a prior contracting phase hands off to expansion through a controlled reversal, and the first usable time may be defined across the bounce by fields that remain smooth even as the geometry turns around. In pyrotic scenarios, a slow, ultra-smoothing contraction replaces inflation's fast stretching, and time becomes reliable, not because space ballooned, but because contraction ironed away inhomogeneities before a transition. In quantum cosmology approaches, the universe is assigned a wave function with specific boundary conditions, no literal edge in time, but a rule that selects histories that are smooth at small size. So first tick is the moment classical behavior emerges from an initially quantum description, the slice where probabilistic interference stops scrambling the very notion of a clock. Whatever the mechanism, the test is the same: reproduce the measured flatness, the near uniformity with tiny, nearly Gaussian ripples, and the pattern of those ripples across many scales, all while delivering a shared time that observers stitched into the later universe would recognize. Evidence for how well the first tick was set is written in the cosmic microwave background, the afterglow released when the plasma thinned enough for light to travel freely. The way that glow is mottled on the sky, the heights and positions of its acoustic peaks, records the statistical properties of those primordial ripples, with exquisite sensitivity, telling us that the initial fluctuations were almost, but not exactly, the same across scales and that they were very nearly random and featureless in their phases. Large-scale galaxy surveys extend the record by showing how those early fingerprints grew into today's web of clusters and voids. And both lines of evidence point back to an origin in which the seed pattern was simple, the background nearly flat, and the clock had already found a common rhythm across distances that are now hundreds of millions of light years apart. If you step one level deeper into what counts as a clock, the expansion itself becomes your master timer. The Hubble rate, the fractional speed at which distances grow, sets a natural cadence, and physical processes line up against it. At early times when expansion is rapid, only the quickest interactions keep up. So species fall out of equilibrium in a well-ordered sequence that cosmologists use as milestones. First neutrinos decouple. Then nuclear reactions freeze out and set the light element abundances. Later electrons combine with nuclei and release the microwave background. Each of these transitions reads the same cosmic wristwatch. And because the order and timing depend on temperature and density, they let you check whether the first tick was set where theory says it should have been. The remarkable agreement between predicted and observed light elements, and between predicted and observed microwave features, says that from the moment clocks were meaningful, the universe's bookkeeping has been consistent. Still, the hardest part remains honest. Why those initial conditions, calling on inflation, explains many traits, but pushes the question to what set the inflating state, and why its quantum jitters had the particular amplitude and spectrum we see. Bouncing pictures inherit their own boundary questions about what made the prior phase so smooth, and how entropy was handled across the turnaround. Wave function proposals must justify why their selected histories look like ours, and not countless others. This is not a failure but a frontier, and you can track progress by watching which models make distinct, testable predictions, subtle patterns in the sky, small departures from perfect randomness, traces in the polarization of ancient light, and survive increasingly sharp data. If you want a rule of thumb to carry away, let it be this: the first tick is not a singular bang on a cosmic drum, but the onset of shared, reliable timekeeping. When expansion, temperature, and interactions conspired to give all honest clocks the same beat. And the initial conditions are the terse instructions that made that beat possible. Be smooth enough to define a common frame. Be flat enough to avoid geometric bias. Be laced with gentle ripples to seed later structure. And be extraordinarily low in gravitational entropy, so that the universe could grow more specific as it aged. Everything else, the stars, the chemistry, the days you count, unfolds from that brief rubric. And there is a soft, human echo in this picture. Beginnings matter, not because they fix every detail of the future, but because they set a clock and a direction that countless processes can trust, a quiet cadence under the noise. In your own projects and plans, the lesson is humble. Choose a clean start when you can. Simple rules that many parts can follow, and a frame where different observers will agree on progress, and the seconds you count afterward will be steadier. Not because time is kind, but because you gave it a stage on which keeping time makes sense at all. Do we need time or just change? Put your watch down for a moment and ask the unsettling question you rarely let yourself entertain. If every fact you can measure is ultimately a comparison between one change and another, do you need an independent substance called time? Or do you only need a reliable way to line up and count changes? You can feel the answer in your hands before any philosophy enters. Every clock you have ever trusted is a carefully trained change, a pendulum trading height for speed, a quartz crystal flexing under an electric whisper, atoms swapping internal configurations in a steady rhythm. None of them contains time as a fluid. All of them provide a stable sequence you can compare other processes against. Once you see this, ordinary physics looks different, but more honest. The equations that predict motion often permit you to label the unfolding with any parameter that moves steadily forward. Because what they truly conserve are relationships among variables, not their position along an external timeline. And in practice, you pick whatever change is simplest to monitor and promote it to time. The moving Sunday for farmers, the motions of planets for ephemerides. When calendars matured, the oscillation of cesium when electronics demanded more regularity. The deeper theoretical versions of this idea strip the scaffold further and show you that a complete closed description of a world can be written in a way that never mentions an external tick at all, insisting only that the set of allowed configurations and the rules linking nearby configurations produce consistent histories, so that what you call past and future are paths through a space of possibilities, rather than points along a universal river. You can make that less abstract by imagining a universe that is, at its deepest level, a book of snapshots with an internal grammar that says which pages can sensibly follow which. To do physics inside such a book, you choose a subsystem. Call it a clock, whose changes are regular enough to serve as a ruler, and then you express the changes of everything else relative to the state of that clock. If the grammar is consistent, you can pick different clocks. And, after doing the translation, you will tell the same story about what correlates with what. So long as your choices are monotonic and precise. The drama of time, then, is a drama about how good a given subsystem is at being that ruler, how insensitive it is to nearby noise, how widely it can be consulted, how easily its ticks can be compared and transported. And the march of timekeeping technology is nothing but the engineering of better, more universal rulers of change. This perspective reshapes the famous puzzles about flow. In a closed ideal description, there is nothing that literally moves from past to future. There is only an ordering of configurations with a rule for how strongly one predicts the next. Why then do you feel a stream? Because you are not outside the book. You are a system that writes and updates records. And the way memory works is inherently asymmetric. New records accumulate, while old ones are rarely erased in an exactly compensating fashion. And your nervous system stitches successive sensory updates into a scene by integrating over short windows and suppressing contradictions, creating a smooth narrative of motion from a sequence of changes. If you doubt this, notice how your experience of motion degrades when the updates are irregular, under a flicker of lights or in jerky video, and how serenity returns when the updates regain cadence. Your sense of the now is the feeling of those updates syncing, not the detection of an external fluid passing by. The same relational lens clarifies how you can do precise science without a master clock. Astronomers once used the mutual changes of planets to define a timescale that made their equations simplest, a kind of time distilled from consistent celestial choreography. In laboratories, you achieve something similar by selecting a transition whose frequency is both stable and widely accessible, then building an infrastructure that distributes that change as a common reference. At no point do you need a metaphysical ingredient, only a standard that many processes can agree to reference. The reason you prize some standards over others is that they are less entangled with the messy environment, drift more slowly, and can be reproduced in many places. Properties that make the translation between different choices straightforward and the predictions portable. If all of this sounds like a trick that might collapse when you push it to the frontier, try it on the hard questions. In cosmology, you define a shared time by the expansion of the universe itself, the change of the scale factor and temperature, because those changes are global and monotonic over colossal intervals. In particle physics, you talk about lifetimes and decay rates, which are themselves stable patterns of change that let you tag processes and compare them across experiments. In strongly interacting matter, where no simple particles exist, you use correlation functions that track how one change echoes into another as your internal clock. And you call the slope of those echoes your timescale. In each case, what you need to make predictions is a robust comparator, not an independent essence. What then of the arrow? Why should change feel directed? The sober answer is that the universe began in a configuration that left enormous room for records to accumulate, structures to form, and details to be written. And that gives many independent subsystems a consistent way to build and keep memories, turning correlation orderings into a shared sense of before and after. But you do not need to revisit cosmology to use that arrow. Every time you compute, you move from a simpler representation to a more detailed one, and rarely the reverse without effort. Every time you measure, you correlate a system with an instrument in a way that is easy to do and hard to undo. Every time you compress data, you use knowledge to trade apparent randomness for shorter descriptions, and that knowledge is itself the residue of earlier change. So the arrow you live within is sustained by practical asymmetries in how change propagates and is recorded, not by a river that flows according to a calendar. There are honest limits to the just change mantra you should keep. If you choose a poor clock, one that wobbles with the very process you are trying to study, your relational description will blur, because your comparator is part of the noise. If you try to compare changes across regions that have weak or delayed causal contact, your synchronization becomes model-dependent. And you must carry those assumptions explicitly, and if you ignore the cost of making and preserving records, you will smuggle in a preferred direction without admitting it. None of these are metaphysical failures. They are engineering cautions. Pick good rulers, state your translation rules, track your bookkeeping when you put the pieces together, and let the room get quiet. The answer you carry forward is modest and empowering. You do not need an extra substance called time to do physics or to live coherently. You need consistent change and a standard against which other changes can be compared. Call that standard a clock if you like, but treat it as a subsystem with strengths and weaknesses, not a deity. Then the world's equations become instructions for how patterns of change forecast one another. Your instruments become negotiated translators among those patterns, and your sense of the day's flow becomes the felt rhythm of updates arriving and being woven into memory. Begin gently by noticing that every claim of how long hides a comparator. Step deeper by choosing comparators that make your questions sharp and your predictions stable, and end softly with the recognition that what deserves your care is not an invisible river, but the quality of the rulers of change you build and share. Because with good rulers, change writes a legible story, and time is simply the name you give that story's reliable order.